Hello everyone and welcome. I am Ani, HR Manager at Espressif Systems.
And I'm Sonika, Embedded Software Engineer here at Espressif Systems. It's great to have you all with us.
Today marks the beginning of Espressif DevCon25, our annual online conference with a deep dive into the latest developments, tools, and ideas shaping the future of connected devices.
We are coming to you live from Brno, Czech Republic, a city known for beautiful architecture, historical landmarks, and great food. Today, we will be the host for the 4th edition of Espressif DevCon.
So let's give everyone a quick overview of the DevCon structure this year.
Yeah, sure, Ani. So this year's DevCon is a 2-day event. Day 1 is packed with 13 talks, including a keynote. Each presentation will last for 25 minutes, followed by 5-minute live Q&A session, where speakers will answer as many of your questions as possible. You can also participate in the live chat throughout the day.
And then we have day 2, which is all about live interactions. We'll host a full live session, giving you the opportunity to engage directly with us, explore the latest features, and dive into topics you care about the most. No QA, everything happens live and in real time.
Wow, that's amazing, Annie.
It is.
I have heard that this live session will be conducted by Ivan Grokotko. Is that right?
Yes, you are right. And talking about him, this year, keynote speech will be done by Ivan, our Vice President of Platforms. So let's welcome him for welcome words and keynote speech.
Hi everyone, my name is Ivan Grohotkov. I'm VP of Software Platforms at Espressif. Welcome to Espressif DevCon25. Since our last developer conference, we've been busy on many fronts, launching new products, releasing new versions of software, improving security, and expanding the ecosystem. Let me give you an update on our progress, starting with the chips. Over the past year, 3 new SoCs have gone into mass production. First, the ESP-32P4, our high-performance microcontroller with dual-core RISC-V processor running at up to 400 MHz. ESP-32P4 is aimed at HMI applications, edge computing, and any application that requires rich I/O. Support for ESP-32P4 is already available across our SDKs and frameworks, including features such as hardware-accelerated H.264 encoding, graphics acceleration, and offloaded Wi-Fi connectivity using chips such as ESP32C6. Next, the ESP32C5. It's the industry's first RISC-V SoC with Wi-Fi 6 on both 2.4 and 5 GHz bands, plus Bluetooth 5 and IEEE 802.15.4 for Thread and Zigbee. ESP32C5 is a great option for multi-protocol, low-latency applications. It also supports external PS RAM, which allows for more feature-rich applications and gives more breathing room for future software upgrades. And third, there is the ESP32C61, which brings affordable Wi-Fi 6 and Bluetooth 5 connectivity, again with optional external PS RAM. It's designed for cost-sensitive products that do require large amounts of RAM. Now, let's take a look at what is coming next. The ESP32H4 is our next generation low-power SoC with 802.15.4 and Bluetooth 5.4 LE. Compared to Bluetooth 5.0, it offers much lower power consumption and unlocks new use cases such as LE audio, PAWR, and direction finding. The ESP32H21 is a low-power variant of the H2. It is aimed at battery-powered sensors and small devices that rely on 802.15.4 and Bluetooth LE. And finally, our first Wi-Fi 6E product. It supports 6 GHz band, 160 MHz channels, and runs as a 2x2 MIMO multi-protocol transceiver. It's built for high throughput and low latency. This is also our first product with Bluetooth LE 6.0 and BR/EDR support. On the security side, we've also made good progress. The ESP32C3, S3, and H2 have all received PSA Level 1 certification. The C6 became the industry's first RISC-V MCU to achieve PSA Level 2, which is a big milestone for our affordable security goal. With ESP-TEE, we now isolate crypto operations inside a secure environment. TEE stands for Trusted Execution Environment, which helps with secure Matter integrations and generally raises the security baseline for connected devices. We also published detailed RED DA compliance guidance, including a self-assessment tool to help customers meet the new European wireless regulations with less guesswork. In parallel, we've been investing a lot of time into improving the developer experience, both for application developers and for people who build reusable components. In ESP-IDF 6.0, our next major release, we are introducing, for example, a new version of the CMake-based build system. It's more flexible, it integrates better with standard CMake projects, and makes third-party code reuse much easier. In this build system, the component dependencies can now depend on kconfig options, which opens the door to more modular and more configurable designs. Our component registry has grown to host over 1,000 components. It now also provides the MCP server, so coding agents and other AI tools can automatically find and pull the components based on the project needs. We've also been working on ESP-IDF installation process, which historically has been inconsistent between command line tools, Windows installers, and IDE plugins. We're consolidating everything into a single tool called ESP-IDF Installation Manager, and we are updating the documentation and IDE integrations to use this unified workflow. Inside the ESP-IDF and the registry, we continue to add new building blocks for more complex IoT applications. For example, we made updates to our USB driver framework. We added new secure DNS and Ethernet driver components, improved 4G modem support, and added many new core features like binary format logging and over-the-air updates for the bootloader. This is just a small portion of the new features that we've developed during the last year, and we will share many more during the DevCon. For Matter products, our ESP Matter SDK is now Matter 1.4 ready, and work on Matter 1.5 is underway. Matter 1.5 adds new clusters and new device types, including cameras, and we support those. We also have our Rainmaker camera solution, which gives developers another way to build secure cloud-connected video products. Based on the feedback we got from our ESP-0 solution, we are addressing the needs of device makers who want a fast way to get a working Matter product, but require more customization than zero code can provide. So we are introducing ESP-LowCode framework for building production-ready Matter devices. There is a full talk about this later in the conference. We are also releasing the ESP Rainmaker App Development Kit. It's a TypeScript-based toolchain for building hybrid iOS and Android apps that integrate with Rainmaker Cloud. The goal is to make app development for connected products faster and more predictable. On the multimedia side, ESP-GMF and our UI framework Brookesia have both matured a lot, and they now allow for more advanced, visually rich applications on the ESP32S3 and the ESP32P4. Alongside of all this, our existing coprocessor solutions such as ESP-hosted, ESP-ATE, ExpressLink, and ThreadRCP continue to fill important roles for customers who prefer a hosted or a modular design. We are also actively working with other ecosystems. We have released the version 1.0 of ESP-HAL, which is the first official SDK for embedded development in Rust language offered by a chip vendor. ESP32C6 support is now upstream in Zephyr, and work on ESP32P4 in Zephyr is ongoing. Our Arduino releases stay aligned with ESP-IDF chip support, meaning that new targets such as ESP32P4 and ESP32C5 can also be used by Arduino developers. We also continue to improve support of our new chips on NUTX, And thanks to NATEX's strong POSIX layer, we even have full CPython interpreter running on Espressif hardware. Earlier this year, we introduced our documentation chatbot, which gives authoritative answers directly from our docs. It has already served more than 100,000 queries, and it's quickly become the first stop for many developers when they have a question. Speaking of documentation, we have launched the new documentation website, documentation.espressif.com, also known as CDP. There, you can find datasheets of chips and modules, technical reference manuals, user guides ranging from developer boards to software packages, as well as product documents such as certificates, advisories, and PCNs. We have also published over 60 articles at our developer portal, developer.espressif.com. Over at the developer portal, we are not only announcing new releases, but we are also sharing tutorials, practical guides, and even workshops. Another notable thing that happened since our last DevCon is the increase in the capabilities of AI coding agents. In many practical cases, we see that tools such as GitHub Copilot, Claude Code, and Cursor can greatly help developers in their work. When writing code for Espressif chips, AI agents perform quite well thanks to the large number of open source projects written for Arduino and ESP-IDF published online. Now that these tools and IDEs combine LLMs with access to project codebase and the development tools, complete end-to-end workflows become possible, including developing new features, increasing test coverage, doing refactorings and bug fixes. Since most of the functionality of our SDKs and frameworks is available in the form of CLI commands, compiling, flashing, running unit tests, agents are already capable of helping you with many development tasks. On top of that, we are building MCP servers to help integrate the SDKs, tools, examples, and documentation better into these workflows, improving the results. We are also working on something new in the area of AI agents. It will help customers build simple voice interactive systems, app-based customer support tools, and agents that bring intelligence into connected devices. We will share more on this soon. All of these efforts make developing with Espressif hardware faster, easier, and more powerful than ever before. Our goal is to provide affordable, secure connectivity for everyone. We are proud of what we've built, and we are even more excited about what comes next. Thank you all for being part of our developer conference, and I hope that you enjoy the event.
What an amazing keynote from Ivan, and I really enjoy how he talked us through all the new products and development coming from Espressif. Super motivating, and I love how he tied everything together, especially the new HMI solutions, including the one we are about to hear more, Brookesia.
Exactly. And speaking of Brookesia, not just the framework, but the animal. It's one of the smallest chameleon in the world, famous for adapting to almost anything around it. Tiny, flexible, and surprisingly powerful.
Which makes the name perfect because our next framework aims just to be as adaptive. We are excited to welcome Zhongwei, who will introduce ESP-Brookesia, a modular framework designed for AI interactive products.
Brookesia bridges UI and AI on the ESP platforms, supports multiple AI agents, and keeps everything portable, thanks to standardized service interfaces. Just like the chameleon, it adjusts naturally to different hardware environments.
Zhongwei will walk us through the core architecture, the development workflow, and real-world examples of Brookesia, powering the next-generation AI-enabled devices.
So let's jump right into it. Please welcome Zhongwei.
Hello everyone, my name is Liu Zhongwei. I'm an embedded software engineer in the HMI Application Solutions team at Espressif. My primary responsibility is the design and the maintenance of the ESP-Brookesia framework, and I'm honored to share our work with you today. My presentation will be structured into 5 main parts. First, an overview of the ESP-Brookesia framework. Then, a detailed look at its 3 core components: the service framework, AI interactive capabilities, and the system plus app framework. Finally, I will discuss our future plans. So what is ESP-Brookesia? In a nutshell, ESP-Brookesia is a modular software framework for AI interactive products, offering a unified solution that seamlessly integrates UI and AI on ESP platforms. It supports multiple AI agents and provides unified service interfaces with high portability across hardware. It has 4 key characteristics. First, primarily developed in C++, leveraging object-oriented and modern C++ features. Second, provides a plugin-based unified service framework for flexible function management and modular integration. Third, delivers comprehensive AI interaction capabilities, including support for various AI agents and a rich expression system. Fourth, employs a system plus app development module, separating system and application logic for easier extension and maintenance. Finally, about the name Brookesia, is a genus of chameleon known for its camouflage and adaptability. This perfectly reflects our framework's goal to build a flexible and scalable AI application solution capable of adapting to various complex requirements. What you see now is the overview architecture of ESP-Brookesia. We have clearly divided into 3 layers: the higher layer, the middleware layer, and the application layer. Components shaded in green reside within our Brookesia repository. Let me talk you through it from the bottom up. The bottom layer is the higher layer, based on the familiar ESP-IDF, handling fundamental hardware operations. Above it is the middleware layer, which aggregates functional components provided by the ESP registry. For example, ESP Board Manager enables rapid hardware board porting. LVGL and ESP-LVGL adapter deliver comprehensive UI capabilities. ESP-Boost provides standard C++ development utils. ESP-GMF handles audio-related functionalities. Built upon this is the core of our architecture, the service framework. It plays a pivotal bridging role. It can call upon here or middleware capabilities below. We are providing unified operational interfaces to the application layer above, and it supports flexible plugin-based extension. Currently, Brookesia has implemented services including Wi-Fi, audio, and NVIs. The top layer is the application layer, which directly provides AI system and app-related components for developers to use. Next, I will delve into the design details of these core components. First is the service framework. Let's first clarify the rule of service within the framework. You can see that Brookesia Service Manager component acts as a bridge connecting the middleware and the application layers. It is dependent upon both the various functional services on the left, like Wi-Fi, NVS, audio, and the app-layer applications on the right. These functional services, in turn, directly call the required hair or middleware components to implement specific features. The key benefit is when developing applications, we no longer need to depend directly on the hair layer. Therefore, we can summarize the rule of service in 3 points. First, upward. Provide unified interfaces for applications, simplifying development. Second, downward. Directly call hair functions to implement features. Third, ultimate goal. Achieve decoupling between the hair layer and the application layer. So how is this achieved? I will focus on 2 key designs. The first is the plugin-based mechanism. We implemented a generic plugin functionality in the Brookesia LibUtils component for automatic registration and management of components sharing a common base class. As shown, the macro at the bottom encapsulates the registration functionality. The Brookesia Service Manager provides the base class for all services. Functional services like audio simply inherit from this base class and use the plugin macro for automatic registration. The Brookesia Service Manager uses the plugin registry class to manage all registered plugins uniformly. Though through this mechanism, the application layer only needs to explicitly depend on the Brookesia Service Manager component, achieving dependency decoupling from the hair layer at the component level. The second point is the unified interfaces. We implemented JSON RPC functionalities based on both ASIO and TCP socket, using a user information service as an example. Applications and services interactive using a client-server architecture. Applications send requests and subscribe to events via the client. Services return responses and publish notifications via the server. The Brookesia Service Manager provides an I/O context for synchronous scheduling for both sides, with TCP socket as the unified communication carrier. The services specifically support 2 operation modes. The first is RPC call. The application calls call function, passing the service name, function name, and the JSON parameters. The client packages this into a request packet and sends it. The server passes the packet, invokes the corresponding function, packages the result into a response packet, and sends it back. The second is event subscription and publication. The application calls subscribe event to subscribe to a specific event. The server records the connection. When the event occurs, it passes a notification packet to all subscribers. Upon receipt, the application triggers the preset callback function. In summary, this unified interface is thread-safe and non-blocking, achieving decoupling between the application and the HAL at the code level. However, please note, because this framework relies on asynchronous scheduling and TCP communication, it is more suitable for scenarios involving small data volumes and not requiring high real-time performance. Next up are the framework's AI interactive capabilities. Brookesia's AI capabilities are primarily composed of two types of components: AI agent and AI expression. AI agent responsible for communicating with cloud agents via protocols like WebSocket, supporting voice interaction, and publishing events like expressions and text through the service framework. Currently, we have implemented components for Codes and OpenAI, and with Remaker and Xiaozhi under active development. AI expression provides typical AI expressions like happiness, anger, sadness. It uses Espressif's custom EAF codec for facial animation playback and offers expression control via the service framework. We have implemented the emote component and provide an online EAF convention tool to easily convert GIF files into the EAF format for use. Finally, let me introduce the System plus App framework. Brookesia currently includes two built-in systems, phone and speaker. First, the phone system features a smartphone-like UI, primarily targeting products with rectangular touchscreens. It has unified interaction logic, supporting interface switching via a navigation bar or gestures. Furthermore, it supports dynamic installation and uninstallation of apps and can manage the coexistence and UI of multiple background apps. The speaker system, built up on the phone foundation, is AI interaction capabilities. It mainly targets touchscreen equipped smart speakers or smart toys, incorporating a voice interaction agent module and an emote module for visual expression display, aiming to deliver a more nature and emotionally engaging interactive experience for users. Using the phone system as an example, it has two key designs. First is stair-sheet mechanism, which ensures the system adapts to screens with different resolutions. Its implementation can be summarized in 3 steps. First, data abstraction. Parameters related to display and interaction depend on resolution are abstracted into a unified stair-sheet class. Second is stair registration. Application can implement corresponding stair-sheet objects for different resolutions. Phone comes pre-built with multiple style sheets. Users can also register custom ones. Third is automatic matching. Upon startup, the system automatically selects and applies the matching style sheet based on the actual screen resolution. On the right, you can see the phone system utilizing the mechanism to display correctly on several different resolution screens. The second key design is APP development and management. Brookesia provides a unified development and management mechanism centered around apps, standardizing their life cycle. Events like run, back, close, pause, and resume. Let's look at a simple app example. All apps inherit from a unified base class, which defines virtual function interfaces triggered by specific interaction actions. Among these, run is the most important interface called when the app is entered for the first time, used to create the app's UI interface. Regarding UI creation, we support two methods. Method 1, when the app enables the default screen, it can directly acquire and use the blank screen provided by the system. This is the most common LVGL development approach. Method 2, when the app disables the default screen, it needs to manually create a new screen. This fits perfectly with the CLion Studio workflow. Simply place the exported source file into the app component and make some modifications to get it running. The right side shows the main program flow. Instantiate a system object, then add and activate the system style sheet, then start up the system, finally initialize and install apps. There are also two ways to install apps. First is from registry, achieved by the plugin macro. This doesn't require including app headers fields in the code, achieving decoupling. The app example on the left uses this method. Second is by instance, requires manually creating the app instance and installing it. This requires including the app header field, creating a code dependency. Furthermore, thanks to the unified service framework, individual apps do not conflict in terms of component dependencies or underlying costs. They can be developed independently and integrated easily, allowing us to combine diverse UIs and application functionalities within a single project. Finally, let me share the future plans for the Brookesia framework. Our plans focus on four main areas. First is enrich functional modules, continuously add more services, agents, and app components. Second is introduce runtimes, incorporate runtime environments like WebAssembly and MicroPython in the middleware layer to support app development using scripting languages. Third, explore new UI methods. Investigate descriptive UIs, such as using LVGL Pro and XML to enhance the style sheet mechanism. Fourth, optimize product projects. Continuously improve the framework's portability, enabling it to run flexibly on various third-party development boards to meet customization needs. That's all for my sharing. Thank you for watching.
That was a really interesting deep dive into Brookesia. I love seeing how UI and AI can blend so naturally when the framework adapts as well as a tiny chameleon. It definitely opens the door for some exciting product ideas.
Absolutely. And speaking of exciting product ideas, our next talk moves us into the world of smart vision, which is becoming a bigger part of modern IoT devices every year.
We're happy to welcome Wang Xun, who will show us how to get started with ESP-Video-Components, a solution built specifically for camera-based application on the ESP32 series.
Yes. In this session, Yuxin will walk us through the typical application scenarios, explain how to use ESP video, and give an overview of the framework that ties everything together.
So if you ever wanted to add vision capabilities to your ESP project, from simple image capture to more advanced camera pipelines, this talk is a great place to start.
Let's welcome Wang Yuxin. Yuxin, the stage is yours.
Hello, everyone, and thank you for joining the session on building smart camera applications with ESP Video. I'm Wang Yuxin, an embedded software engineer at Espressif. Let me start with a question. How many of you have spent hours, maybe even days, trying to get a camera software to work with your embedded project? Dealing with different interfaces, driver configurations, timing settings, it can be quite challenging, right? That's exactly why we built ESP Video. Simply put, ESP Video is a software component that helps developer easily obtain image data from camera sensors. For example, with the ESP32P4, you can simultaneously operate multiple cameras connected to MIPI, DVP, USB, and SPI interfaces. So what can you build with ESP Video? At the basic level, you can capture images and send them to a phone or the cloud. For more advanced operations, you can pair ESP Video with our ESP-DL and ESP-WHO components to aid AI capabilities like face recognition, color detection, motion detection, and barcode scanning. Imagine smarter retail systems that identify products automatically, or circuit cameras that detect movement. In all those cases, ESP Video provides the stable camera foundations that those smart features rely on. What if you need more than one camera? No problem. ESP Video supports multiple camera connections simultaneously. For instance, you could connect 2 cameras to monitor a conference room from different angles. Whether you are building a simple single camera app or a complex multi-camera system, ESP Video can handle both scenarios. Now, you may be wondering, why use ESP Video when I could work directly with Firmware drivers? That's an excellent question, and it gets heard of very correct ESP Video. The challenge is that camera interfaces very widely. SPI, DVP, MIPI CSI, and USB, each suited for different scenarios. For low-resolution applications, SPI or DVP cameras offer better cost efficiency. For high-quality image needs, MIPI or USB interfaces are more appropriate. ESP Video solves this by unifying those complex interfaces. You simply call the open function to open the camera. This approach is much simpler and more universal than directly operating low-level drivers. But that's not all. Real-world camera applications often go beyond basic image capture. Many scenarios require optimizing image quality by adjusting SP parameters, like brightness, contrast, or noise reduction. You may also need to manage multiple data streams simultaneously. For example, sending the captured image to an LCD and storing the encoded image on an SD card. ESP-Video provides higher-level interfaces that simplify those complex operations, making it easier to manage multiple devices and data streams. This lets you focus on application innovation rather than hardware complexities. Now, let's see where ESP-Video fits in overall camera application architecture. As you can see, the architecture has 4 layers. At the top, your operation logic. Then the middleware layer, where ESP-Video resides. Below that, the device layer, and finally, the hardware drivers from ESP-IDF. ESP-Video serves as a bridge in the middleware layer, connecting your operation needs with the hardware capabilities. At the device layer, there are some key subcomponents. ESP as camera as sensor provides drivers from camera sensor and ESP-IPA for image processing algorithms, and ESP-LCD NTF for camera control. Together, those components enable ESP-Video's core functionality, making camera connectivity and image processing significantly easier. So, how do you actually use ESP-Video? Let me walk you those 3 simple steps. Step 1, open the camera. Each camera has a unique name, like Video 2 for DVP connector camera. Step 2, send the control command through L control. For example, request memo buffers by using requbuffer command, and start the data stream by using stream-on command. Step 3, manage image data using dequibuffer and qubuffer commands. Specifically, use dequibuffer to retrieve a frame buffer from the queue, process it, then use the qubuffer to return the buffer for the next frame. Here is a real-world example. We connected USB, DVP, and MIPI CSI cameras to an ESP32P4U board and streamed all 3 feeds simultaneously to a web page. You can find this and other examples in the ESP-Video examples dictionary. That concludes my presentation. If you encounter camera integration challenges in your projects, I encourage you to try ESP-Video. We welcome your feedback and expressions as we continue to improve this community together. Thank you.
That was a great session from you, Hin. It's always impressive how much capability you can squeeze out of ESP32 when it comes to smart vision. The whole ESP video ecosystem really opens the door to do some fun experiments.
That's definitely true. And now we are shifting gears from cameras to something every developer can appreciate, making our workflow smarter. Because who doesn't want to spend less time in clicking buttons and more time in building actual things?
Our next speaker, Brian Ignacio, is going to show us exactly how AI can boost productivity when you are working with ESP-IDF.
Brian will introduce how ESP-IDF extension for VS Code can perform common tasks like building, flashing, monitoring directly from the chat interface using AI agent mode.
And he'll also demonstrate how to use these features not just in VS Code, but in other AI-assisted environments like Cursor, giving you even more flexibility in how you develop.
So, if you have been wondering how AI can streamline your ESP-IDF workflow, this is perfect talk to watch.
Let's welcome Brian Ignacio. Brian, the stage is yours.
Hello, my name is Brian Ignacio. Today we're going to see AI in ESP-IDF, leveraging agent mode with the ESP-IDF extension for Visual Studio Code. A little bit about me. I'm Brian Ignacio, one of the maintainers of the ESP-IDF Visual Studio Code extension, the ESP-IDF web extension for Visual Studio Code, and the ESP tool.js. I'm also part of the IDE team, helping Espressif users to simplify the user experience and onboarding to the ESP-IDF. Today, we're going to see how this feature works and how can you use it. So first, this feature uses the LLM language tool API from the Visual Studio Code. This allows us to extend the agent mode with domain-specific tools from the user prompts in the Copilot chat. This allows us to leverage the task output from the ESP-IDF extension to be processed by LLM, allowing us to further debug or do some additional tasks to the already existing features that we implement in the ESP-IDF extension. Let's take a look at that. So they have a few available commands. So these are the commands that we have implemented on as of now in the integration. You can build specific partitions like app, bootloader, partition table. You can flash. You can also flash specific partitions and using a specific flashing types like flash app, flash bootloader, partition table, using UART, JTAG, DFU. You can also monitor. You can also trigger the build flash monitor command. You can also pass specifically for what you want to build in Flash, like app bootloader partition table, and the flash type that you want to use. You can also run the full clean. You can also set target and specify which target you want to use. These are the ones supported as of now. And there are also additional commands. These commands will basically just trigger the UI launch. So for example, menu config, this allows you just to launch the UI for menu config, as we call in the extension, the SDK config configuration editor. And other UIs, such as the size. We can also run the erase flash task will be an output. You can also select the serial port, run the doctor command, open the new project wizard, open the partition table editor, open component manager, app trace, heap trace, etc. So how do you use this new feature in the ESP-IDF extension from the VS Code Copilot chat? So the steps to use are quite simple. You can just use some natural language to run specific commands. But in order for this to work, make sure that you have installed the ESP-IDF extension and the ESP-IDF is configured within the extension itself. Now open a ESP-IDF project, then press the menu view, and then open chat. This allows you to see the chat, the Copilot chat. After that, just type the command, build the project, and then you will see a notification saying confirm ESP-IDF command. This is basically to make sure that you know what you're doing. So After that, you click allow to let the command start running. Then after that, you will see an input. You will see what is the chat interpret from here. And you will see the output of the command that you have executed. So for example, here I have two examples. First, you have an explicit function call or the tool that you're calling. So you do hashtag ESP-IDF commands, build, and app. And this is an explicit way to call the build for the app partition. So as you see here, the input is, it will take the build, it will take the app as the partition to use, and it will execute this. It will just build that partition here. You can also do the same. We're using natural language, just like build bootloader. And the LLM will interpret this as you're trying to build, and you're just trying to build that bootloader partition. And you can see it's just building that specific partition table. So after that, this is the previous case was a successful case, but we can also use LLM to our advantage. For example, when we have build errors and something happens when we are trying to build, you can try to build a project, for example, using whatever natural language or the specific command with the hashtag ESP-IDF command. And in this case, we have show an example of when you have an error. So you can see here in the output, this build has failed because it has an error. So the error here, sorry, I have to split the screenshot so you can see the whole thing. This is part 1 and this is part 2. You can see here that this has failed, and that the reason why it has failed is because the partition, the flash size is too small, the configured flash size in your SDK config. So you can see that the LLM has interpreted the output, and it tells you the error, that it has failed because partition table has 2.1 megabytes of flash, but it is the configured flash size is only 2 megabytes. So you need to update this value in the menu config, and provide you some steps to do that after that. So now let's take a look at how can we do this from the VS Code itself. So here, I'll just open here my VS Code windows. Welcome to the VS Code. Then here, I just have already existing project open. So for me to test this thing. As I mentioned you guys here, you can go to the menu view, chat, and it will open this window you have here. Then here you can just type build the project, for example. This command, then it will start executing. You will see a notification, confirm the command. You press allow. You can see that the command will execute in both cases, in the terminal and in the chat. So now the command is running here. You can see the output on real time here. And here is waiting for the command to be completed. So you see it has finished here, executing. And now the build is successful. Now the chat has access to the output here. So you see here, the build is being successful, and the output binary was generated without any errors. If I go here, for example, on the SDK config to demonstrate the previous case, I'll change the flash size to 2 megabytes. I will save this change, and I will try to run the command again. This happens because the project is already built in the context that you have here. So you probably want to run some command to clean the project first to delete the build directory. So you see clean the project, then the project has been cleaned. Then now I can just I will, just for the sake of demonstration, I will show you the explicit command. You see, I type ESP-IDF commands here, then I type build, and this will execute the build command, same as before. Now this will reuse the terminal from before, and the chat will wait for the execution to happen. You see that even the message is built successful here, but in the terminal you can see that there was an error happened here. So, but if you go to the chat, you can see it shows the message that the build failed because the partition table occupies 2.1 flash, but it does not fit the configured flash size. And then you can do some actions here. So you can you can do the configure the project to open the SDK config editor. And this will trigger a UI. This is the same as just running your this command here, SDK config configuration editor. And it will try to it will open this SDK config editor, and then we can update the serial flash. We can update the serial flash monitor. Sorry, the flash size here, and update it to the proper size. Save it, and that's it. There are a few other things that you can experiment here, but just for the sake of this presentation, we can just look at these things. You can also pass, as I mentioned before, you can just execute commands specifically, like set target here, or using the natural language set target to ESP-32C3, for example. And you see here that this command interprets the set target command and the target that you want to execute it. So you see here now the output is running the set target action, and it will update the SDK config file. And yeah, that's it. So that's all for the demo. Thank you for watching. And if you have any questions or suggestions, please reach out to us in the ESP-IDF VS Code extension GitHub repository, or in the QA session we will have now. Thank you for your attention.
Hello, everyone, and welcome to the live Q&A session here at Espressif DevCon 25. I'm Pedro, and I will be the host for all the Q&A sessions you will have here for this edition. And to start with our first session, I'd like to invite to the stage Brian Ignacio. Hi, Brian. How are you today?
Good, good. How's it going, guys? I hope you're enjoying the DevCon.
Yeah, and we have actually people from many different countries here. We have from Ireland, US, New Zealand, India, and Bulgaria. So we have people from many different places. And for some of you, it's early in the morning or late in the night. So thank you, everyone, for watching us in different time zones. And Ryan, actually, from where you're talking now?
We're live from Shanghai, China.
Nice. Yeah, we have Brazil and Finland as well. So yeah, so we have people from everywhere. All right. So since we have no questions from the audience, I like to ask one question that I'm also curious about it, but when this new feature will be available for developers?
So the feature is already in the GitHub master in the repository. So if you want to give it a try, you can just go ahead and grab the BSIX installer from there and help us just finish some testing, see how things works out. So we're just preparing for the 1.11 release, which will have this new feature for you guys. And we are testing the whole extension, trying to make sure that everything is working well. Yeah.
Great. And what's the best way to give you feedback, especially for the users who will test before the final release?
Just reach out to the BS Code GitHub repository for ESP-IDF. We are super active there. We read everything you post. We try to work as fast as we can to fix any issues you guys have. So please reach out to us, and we will do our best to help you out.
Great. And one more question. How are you expecting people to use this AI agent new feature? Do you have something in mind how people should use it, or are you expecting how do you expect people will use?
I think the question is, I don't want to limit the people. I don't think we should limit the people. We just want to allow the user to get that information out from the build from the extension task and to the LLM, so the LLM can help you debug things, debug the build output, debug flash, debug other tasks that you get executed in the extension. And we are working together to extend this to other functionalities so you can understand better what is happening on the IDF and on the extension experience at all. So just if you guys have the chance, please test it. And if you have any feature requests or any suggestions or issues, we are happy to work together and make it better for everybody. That's the goal.
Yeah, so and I think this is a great addition for Espressif ecosystem. It will help a lot of our developers. So I hope you guys enjoy this new feature. And Brian, thank you very much for the talk and as well for joining the live Q&A session. Thank you very much. Okay, so now we can go back to our program, and I will be back for the next Q&A session. Thank you.
Brian really showed how AI can streamline the ESP-IDF workflow. I'm already thinking about how many repetitive steps I can finally stop doing manually. The talk was a productivity lifesaver.
That's true, Annie. And now we are moving from productivity to one of the most important topics in IoT today, which is security. Because as our devices get smarter, the threats get smarter too. And the rules and regulations certainly are not slowing down.
Exactly. Our next session, it's all about building trust directly into your products. We are excited to welcome Loki Hasse and Sachin Bilore, who will introduce how ESP-TEE brings hardware-enforced security into Matter devices.
They'll explain how global cybersecurity requirements are shaping device design, why protecting credentials is more critical than ever, and how ESP-TEE integrates with Matter ecosystem to help manufacturers meet these demands.
And they'll be showing how this works on Espressif RISC-V SoCs, demonstrating how hardware-backed isolation can block scalable remote software attacks, a big deal for anyone building connected products.
This session is perfect for the developers who want to create products that are secure, not just in theory, but in practice at the hardware level.
So let's give a warm welcome to Loki Hase and Sachin Bilore. The stage is yours.
Hi all, thanks for joining in for today's talk on building hardware enforced trust into meta devices with ESP-TEE. So before we start, here is the brief introduction of us. Myself, Sachin Bilore, and I have with me Loki Khasi. We are part of the security team at Espressif Systems. Our team is responsible for developing and maintaining the security features of ESP-IDF framework and ensuring platform level security. This also includes fundamental components such as cryptographic peripherals and other proprietary security IPs which we develop, which support the broader security architectures and capabilities offered within the ESP-IDF platform. So let's start with the agenda. So as you may remember, we had introduced ESP-TEE in DevCon 2024. So we will start with a brief recap of ESP-TEE. We'll continue after introducing ESP-TEE, we continue to integrate ESP-TEE with ESP-TEE product offerings. We started with integrating ESP-TEE into ESP Meta Device Framework to enhance its security profile. This is the main agenda of today's talk, and we will cover this later in this talk. Then we'll elaborate on implementation consideration in integrating ESP-TEE with meta devices and one example demo from the work of this integration. We will also conclude with the current status and future plan of the ESP-TEE with ESP-TEE products. So let's start with the recap of ESP-TEE. So as we had said earlier, ESP-TEE is Trusted Execution Environment Framework on ESP-TEE SoCs. It is hardware-defined and software-implemented framework which enable the trusted execution environment parallel to traditional rich execution environment. In ESP-TEE framework with ESP-IDF software stack runs as a RE and hosts all the regular applications, while ESP-TEE secure software stack execute in parallel as a secure execution environment and host all the secure services and secure resources. ESP-TEE is supported on RISC-V architecture-based Espressif SoCs and use all proprietary or inherent RISC-V architecture security features. Say, for example, privilege modes, physical memory protections, and we also enhance these security features with custom security extensions, which we had discussed in our previous talk on ESP-TEE. ESP-TEE also provides transparent and auditable foundations for regulatory and security certificate compliance, which we will demonstrate or will show later in this talk. ESP-TEE is also configurable and ensure minimum changes in ESP-IDF framework, and it has minimum impact on the regular development framework development workflow. So how ESP-TEE actually enhance the security profile of a device? So ESP-TEE isolate all the security resources and keys and other data, security sensitive data in separate execution environment. This help in countering the software and remote scalable attacks. We had discussed this in little bit detail in our previous talk, and it will be demonstrated how we enhance the security profile of a device later in this talk when we will talk about integration of ESP-TEE with meta devices. ESP-TEE also includes some basic security services which are mandatory for many security certification programs and regulatory compliances. So let's talk about those basic security services. So if you remember, I had discussed this in previous talk that ESP-TEE forms the updatable root of trust, which is rooted in immutable root of trust. And these basic security services are implemented on top of this ESP-TEE, which is updatable root of trust. So these security services actually leverage those assurance level provided by ESP-TEE. So this way, this provide the secure services for the devices while protecting all the secure resources and confidential keys and data. So let briefly enumerate these secure services. First of them is secure storage. It is persistent storage implemented in external flash storage. It is independent of existing flash encryption mechanism, which you may know. The main difference is that here secure storage partition will not be accessible to REE. So any data or information stored there will be inaccessible even in encrypted format also to REE. Second, basic secure services device attestation. So attestation is the mechanism through which a device can identify itself to remote relying parties. It is done by generating and providing the entity attestation token. So ESP-TEE here helps to generate and cryptographically sign this ETA under its protection. So RE can request generating this ETA, which is cryptographically protected, and RE can then provide this to remote relying party, which can verify it and can identify the current status of the device. Third is a secure OTA update. Since ESP-TEE is updatable root of trust, it can be updated using OTA mechanism. And ESP-TEE ensure integrity and authenticity of the ESP-TEE image, which is coming from the OTA, before allowing it to update and run on the device. It also supports rollback in case of ESP-TEE OTA update doesn't pass the verification check. So these are the basic secure services which are part of the default ESP-TEE installation, ESP-TEE support, but based on the device use cases and requirement, some custom secure services also can be added, implemented and added as part of the ESP-TEE framework. So as I was mentioning that ESP-TEE provide transparent and auditable foundation for regulatory and security certificate compliance. So here is this proof of our assertion that with ESP-TEE enable on the ESP-TEE C6 SoC, we were able to, we have achieved PSA level 2 certification. And this is the first risk-based SoC which achieve this certification. So with this level of assurance, when ESP-TEE is supported on the device, I think this framework is ready to meet the future certification and regulatory requirement. For example, upcoming CRA and RATA requirement. And finally, I will talk about future work on the road on the ESP-TEE. So ESP-TEE is already part of the ESP-IDF version 5.5 release. Currently, it support C6 and H2. Support for ESP32C5 and ESP32C61 is work in progress, and it will be supported in upcoming releases. And ESP32P4 support is a work in progress. Along with extending this framework to current and upcoming chips, we have also worked on memory footprint while keeping the performance and stability requirement intact. Since we understand this framework will be executed on the IoT devices which are resource constrained. So special attention we are paying to enhance the memory footprint. So This is brief recap on the ESP-TEE. Now I will hand over this talk to Lokik Hasi, who will elaborate on the integration of ESP-TEE with meta devices. Thanks.
Thank you, Sachin, for the introduction and the recap about ESP-TEE. Let us now continue and understand how ESP-TEE strengthens security in Matter devices. As per the Matter security model, devices rely on two primary key types that must be protected. One is the device attestation certificate, which is the DAC, and the other are the node operational certificates, or the NOCs. The DAC is programmed during manufacturing and used during the commissioning process to prove that the device is genuine and trusted. Commissioning is a process in which a Matter device joins an existing Matter fabric, such as Google Home, Apple Home, or ESP Rainmaker. The NOCs, also called as the fabric keys, are generated at runtime and whenever the device joins a new Matter fabric. These keys are then used throughout the device lifetime to establish secure sessions and encrypt communication within the fabric. ESP-TEE safeguards both the DAC and the fabric keys by keeping them inside a hardware-enforced environment, that is the TE, completely inaccessible to the normal application code. One common way to protect the DAC private key is through the secure storage. In the standard approach, the DAC is stored on the external flash, typically in an encrypted ESP secure certificate manager partition. However, during commissioning or signing operations, the key becomes visible in the memory, which means that if the application is compromised, it could be exposed. With ESP-TEE, however, this risk is completely removed. The DAC is stored inside the T's encrypted secure storage, which is fully isolated from the rest of the system. Any attempt to access this from the RE would result in a fault. All cryptographic operations involving the DAC occur entirely within the TE, and the key never leaves that protected environment. So even if the user application is attacked, the DAC remains secure and inaccessible. Another method for protecting the DAC key is to derive it at runtime using the PVKDF2 algorithm, which is the password-based key derivation function, which uses the HMAC peripheral and the seed material, which is stored securely in the eFuse. This approach avoids storing the actual key anywhere, since the DAC key generated only when it is required. We can see the workflow in the image shown. However, the derived key is still used in the main application context, meaning it becomes accessible or readable in memory during the operation. So even though the seed is protected, the key itself may still be accessible by the application, leaving a small but real attack surface. Now, ESP-TEE strengthens this DAC protection method by taking control of the HMAC peripheral as well as the eFuse key. It performs the key derivation entirely within the TE. The user application can still request signatures or other operations for this key, but only secure service call. It never accesses the key directly. This means that the derived key exists only within the isolated TE. Even if the application layer is compromised, the DAC remains fully protected. Now let's turn to the fabric keys or the node operational certificates. In the traditional setup, as shown on the right, these keys are generated at runtime and stored in an encrypted non-volatile storage type partition, which is the NVS. While they are encrypted, the application still has access to them for signing or encryption operations. This means that if the application is attacked, the keys could potentially be disclosed, creating a security risk. With ESP-TEE, the NOC keys are generated and stored entirely within the TE's encrypted secure storage. The RE never has access to these keys. The TE provides secure service calls, allowing the user application to request cryptographic operations such as encryption, decryption, or signing without ever handling the keys for the RE. This approach ensures strong protection against key exposure or misuse, even if the main application is compromised. Let us now take a look at the implementation considerations of ESP-TEE. From an integration perspective, ESP-TEE fits cleanly into the ESP Matter workflow. It adds only a few system-level components with minimal impact on firmware size or development effort with a substantial security upgrade. To enable it, developers simply need to enable the ESP-TEE keyconfig option through menu-config, update the partition table, and build the firmware as usual. The build system automatically handles the TE firmware generation and signing. Importantly, no code changes are required in the main application. All API remains fully compatible and no other changes are required. With ESP-TEE enabled, there is a slight change in the boot flow. After the second stage bootloader, the TEE runs first and initializes all secure components, including the memory and peripheral protection, heap initialization, and secure storage before the user application begins execution. This flow also accommodates secure OT updates for the TEE firmware. The user application downloads the TEE update, but the TEE handles verification to ensure the update is authentic and safe, and rollback for failed updates. The RE OT update flow remains exactly the same as before. Now, from the numbers perspective, ESP-TEE is designed to be lightweight and efficient. It typically reserves around 36 KB of internal SRAM and about 400 KB of flash for its purpose. But note that both these numbers are highly configurable depending on the use case and the enabled features. Service calls between the TEE and the RE incur only about 600 CPU cycles, which roughly comes about to 3.7 microseconds for the ESP32C6 operating at 160 megahertz. Since last year's beta, we have been optimizing these numbers as much as possible, reducing memory and CPU overhead while maintaining full security functionality. Here is an example demo to see ESP-TEE in action with the Matter device. On the screen, you can see the device, the console output, and the ESP Rainmaker app used for commissioning. We start the commissioning process by scanning the device QR code. We generate and verify the Matter credentials, which is the DAC, and here we can see a log which says the DAC signing operation with the HMAC PPKDF to workflow with ESP-TEE enabled. Connecting to Wi-Fi, and then fabric association. And that's it. The commissioning process is complete. Now we can move on to toggle the light properties directly through the app. We can toggle the state, the brightness, and also the color temperature. Note that the instructions for running this demo will be provided in the video description later. So to conclude, ESP-TEE secures Matter devices with hardware-enforced key management, safeguarding both the DAC and the fabric keys from unauthorized access. Being PSA-L2 certified, it protects against remote software attacks and provides scalable security for all connected devices. ESP-TEE enables secure IoT products ready for tomorrow's deployment scenarios while aligning with regulatory and certification requirements. Thus, security is now built into the hardware from the start, not added as an afterthought, providing a strong foundation for trusted IoT solutions. So here is something from the future integration perspective. ESP-0code is a platform that allows device makers to instantly specify, build, and launch a variety of connected products right through their browsers. So looking ahead, ESP-TEE will be seamlessly integrated into ESP-0code, allowing developers to enable enterprise-grade security from the web console with a single click. The TEE firmware would be managed and updated by IoT by Espressif itself, so developers can focus entirely on the application logic with no extra efforts required. Thus, this will allow manufacturers to deliver PSA-L2 certified Matter devices with minimal effort, combining security, interoperability, and simplicity. So that's it today, folks, from our side. We hope that everyone enjoyed the talk. We'll follow up with a Q&A session soon. Thank you.
And now we are back for one more Q&A session, and I'd like to invite Sachin and Lokik to join us for this live session. How are you guys? So I think you guys are muted. Yep.
Yeah. Hello, guys.
Yeah. Hi.
Okay, so thank you very much for joining the live Q&A and as well for the talk. And I'd like to remind all audience that you must ask questions, and this is very important for us not only questions, but as well suggestions or anything you guys want to share with us today. This is a great opportunity to reach out our engineers live here at DevCon 25. So let's start about the current status of ESP-TEE. Can you guys share about it?
Yeah, actually, as I mentioned, ESP-TEE is available with ESP-IDF release version 5.5 for C6 and H2 SoCs. And as I mentioned, that C5 and C6 one will be ready in upcoming releases. So tentatively, C5 will be available on 5.5.2, and C6 one will be available on IDF release 6.0.
Right, and there is any plan for supporting chips like ESP32, S2, or the previous chips?
Yeah, definitely. We'll try to cover this framework for as many as chip possible. If architecturally it is supported, chip configuration if supports it, and business demand this.
Okay, great. So we have here, hello, Lokik and Sachin. Thanks for the demo. It's really insightful. I had a question related to Matter plus TE. Do you guys have any ready example where I can try out the interface?
So I'll take this. So since this POC that we have developed actually is not a part of the official ESP Matter framework yet, this will be a part of the next release, which will be based on IDF 5.5.2. So then I think you can try this out. But for currently, I think for the demo that has been performed in this video, I think we'll add the steps in the description itself. And for ESP-TEE related examples, you can always, I guess, fetch the 5.5.1 or 5.5.2 IDF releases and try out the TE based examples and let us know if anything else is required.
Okay, thank you very much. And we have another question from the same person here. So I would also love to know about any documentation link, if available, which would allow me to quickly develop Matter products.
Yeah, same, I think when the framework Matter release comes up with TE enabled, I think the documentation will also be updated as required and users will be able to see that. And for general ESP-TEE documentation, it is already been hosted and it is a part of ESP-IDF itself.
Okay, and it's not a question, but this is a message to Aditya. So have you searched for any related articles in Espressif Developer Portal? And actually, we have a couple of articles there. So if you're not aware about Developer Portal, you can go to developer.espressif.com and you can search right in the search bar for ESP-TEE or just TE, and you will find all articles we have there right now related to ESP-TEE. And not only ESP-TEE, but there are many articles out there. Okay, yeah, so we have here the link, developer.espressif.com. All right, so if we have no more questions, guys, do you have anything else you'd like to add before we finish this Q&A session? No. Okay, so thank you very much, Sachin, Laukik, for the presentation and for being part of Espressif DevCon25. Thank you very much.
Yeah, thank you. Bye-bye.
Bye-bye.
All right, we will go back now to the program, and thank you, and see you next on the next Q&A.
That was really insightful session from Lokik and Sachin. Securing Matter devices at the hardware level, it's one of those topics that feels complex, but they broke it down in a very practical way.
I agree, Annie. That was really insightful session. And I think everyone's brain have earned a bit of cool down after that one. So this is perfect moment to take a short break.
Exactly. Now it's great time to grab a coffee, stretch your legs, or get some lunch if that's the time of day where you are.
We will be back soon with more talks lined up for you. So don't go too far. Just enough to refill your mug or maybe check on your latest build.
See you right after the break.
Don't forget to keep your chat alive. We will be back in 1 hour. Thank you.
Welcome back, everyone. Hope you had a good break, whether it was coffee, lunch, or just a moment to breathe. We've got a great lineup ahead, so let's jump right back in it.
And now we are starting with something really fun. Real-time object detection running directly on ESP chips. Yes, the tiny chips we all know and we all love.
Our next speaker is Zhu Wenjing, who will be introducing ESP-Detection, a lightweight and ESP-optimized project built on top of ultra-lightix YOLO 11.
ESP-Detection provides a suite for ultra-lightweight models and a set of APIs that let you train your own custom detection models for your specific scenarios.
These models are optimized for efficient deployment on AI-capable ESP chips, like the ESP32P4 and ESP32S3, enabling cool real-time application, things like cat detection, dog detection, hand detection, and much more.
So, whether you are building a smart camera, a home automation device, or just experimenting with AI at the edge, this talk will definitely spark some ideas.
Let's welcome Zhu Wenjing. The stage is yours.
Hello everyone, my name is Wenjing Zhu. I'm an AI image development engineer in Espressif. Today, I'd like to talk to you about ESP-Detection, a lightweight real-time object detection solution designed for ESP32 chips. First, we will discuss why we need ESP-Detection, what it includes, and finally, I will show some examples and our future plans. Currently, there are already many mature edge vision applications like object detection, classification, and recognition. To build a vision application, we need three essential components: a model, the hardware, and an inference framework. In terms of models, more specifically lightweight models, there are two main directions, the YOLO series and the DTR series, and the YOLO models are more popular in industry. For example, we have YOLO 11 from Ultralytics. We have deployed YOLO 11 Nano, the latest one in the YOLO 11 series on our chips, and use the ESP-DEL for model inference. ESP-DEL is an inference framework developed by our AI team, supporting a variety of common operators. According to the tests, the quantized Intuit YOLO 11 nano model achieves around 26 seconds per inference on ESP32S3 and 2.8 seconds on ESP32P4. This is still too slow for real-time use, where we aim for 50 to 100 milliseconds. Considering the fact that most products only need to detect one specific type of object, we developed ESP-Detection. So, what is ESP-Detection? In fact, it's a GitHub repo. Here is a diagram of ESP-Detection. It has three main parts: models, workflow, and examples. In the models section, we have released ESP-Pico model. While ESP-Nano is still under development, in the workflow part, we cover the whole development pipeline, from model training and validation to model conversion, quantitation, and deployment. ESP-Detection offers APIs so that users can train and deploy their own models. Based on ESP-Detection, we have released several detection examples, including cat detection, dog detection, and hand detection. Examples for logo detection, pedestrian detection, and face detection has not been released yet. Now, let's move on to the workflow of ESP-Detection. First, we need to train a lightweight model. The model structure is defined in ESP-Pico YAML. It's a highly compact model and derived from YOLO 11 Nano model. It has three parts: backbone, neck, and head, with three feature map scales. To achieve real-time speed, small memory, and good detection results, we applied several strategies. We removed the distribution for closed module, as it's time-consuming. We replaced several convolution layers and C2PSA module with depth-wise separable convolutions. We reduced model depths and widths and simplified bottleneck and residue connections. We adopted a lightweight activation function, ReLU, which can be fused with convolution and batch normalization into a single convolution, reducing model latency, and finally, we reduced input resolution. As a result, ESP-Pico has only 0.36 million parameters and 0.17 G-flops at an input size of 224, while YOLO 11 nano model has 2.6 million parameters and 6.5 G-flops at image size 640. We also need to prepare dataset. ESP-Detection is built upon Ultralytics YOLO framework, so it follows the YOLO format dataset structure. A small during training, issues such as false positives on negative samples may arise. This can be reduced by adding more negative samples and balancing their numbers per batch. Well, if collecting your own dataset is difficult, you can start from open source datasets, annotate them using the state-of-the-art vision models, and then check them manually or with a vision language model, like Chain-3 Well, thirdly, since our model is lightweight and adopts low input resolution, disabling mosaic augmentation earlier can help reduce false negatives. Okay, after training, we can evaluate the model on validation dataset. For example, in CAD detection, we use the CocoCAD dataset. We can see from this table that when the input size is 224, ESP-Pico achieves almost the same accuracy as YOLO 11 nano model do, while the inference latency drops significantly. On ESP32P4, about 51 milliseconds, on ESP32S3, about 126 milliseconds. When the input resolution is 416, the mean average precision of ESP-Pico even better than YOLO 11 nano model, which is 0.703 for the CAD class. Including pre-processing and post-processing, the Pico model achieves over 18 FPS per inference on P4 and over 7 FPS on S3. This is a good balance between speed and accuracy. Well, the second step is to export the well-trained model to ONNX format so that it can be quantized into ESP-DL format. First, we need to set batch size to -1 for operations like view and reshape so that the batch dimension is not fixed. Second, we need to change the forward function of ESP-Detect head. More specifically, the bounding box decoding step is moved to post-processing from model forward process. Well, in this way, we have 6 outputs, 3 from bounding box and 3 for logics. We also moved the sigmoid operation of the classification branch to post-processing. You can see the third scale outputs here. Why we do this? Here is the original graph. The bounding box branch and the classification branch are concatenated and then passed to the decoding part. In the decoding part, we have add and sub operators. They adopt joint quantization. So the inputs add or sub share the same quantization scale, but the value ranges of the inputs here differ significantly. If we move this part to post-processing process, it can be calculated in float. So we successfully reduce the quantization error. On the other hand, we can filter confidence first with a threshold impulse processing, so there's less sigmoid calculation and bounding box decoding calculation, which makes model inference faster. Now, after we export the ONNX model, let's talk about the quantization itself. Quantization is a process of converting the weights and activations of a model from high precision to lower precision. For example, on ESP, we commonly convert from float SERP2 to intuit. This picture shows model quantizations. For instance, an activation tensor is mapped from its statistical range to the intuit range. Here is a formula. R here represents the float value, Q is a quantized value, S is a quantized scale, and D is a 0 point. As we just mentioned here, we need the statistical range of a tensor. To collect this information, we need a calibration dataset. It's a set of representative images. Quantization helps us accelerate inference, reduce memory usage, and just lower power consumption and reduce model size. However, it also causes accuracy loss and has some limitation, such as the unsupported operators. After we know about the basic conception of quantization, we also need to know its types. From the perspective of value ranges, we have symmetric quantization and asymmetric quantization. From the granularity perspective, there is potential quantization and per-channel quantization. Potential quantization uses a single scale for all values in a tensor, while per-channel quantization calculates a scale for each channel individually. Per-channel quantization can achieve better quantization accuracy as it's more fine-grained. There is also group-based quantization, but we want to go into details here. From the state perspective, quantization can be divided into post-training quantization and quantization-aware training. We call it PDQ and QAT. Well, specifically, we use the ESP-PPQ quantization. It's a tool based on PPQ from system. And further, we only support the symmetric and potential quantization with power of 2. Well, power of 2 means that the quantization scale is an integer power of 2. This is limited by PIE instruction set that we use. ESP-PPQ offers 2 APIs, ESP-Video-Quantize ONNX and ESP-Video-Quantize Torch. Here we use ESP-Video-Quantize ONNX because ESP-Video-Quantize Torch will convert the PyTorch model to ONNX directly. However, we need to change the forward logic as we just did in the previous step. Once the quantization is complete, 3 files are generated. The ESP-DIO file, an info file, and a JSON file. ESP-DIO file is the binary model file. The other 2 files describe the quantization details, and you can find the supported operators in this link. Okay, we have different quantization methods in ESP-PPQ. The simplest and fastest is intuit quantization. You can use it with default setting. Of course, you can use into 16 quantization or mixed precision quantization. In mixed precision quantization, only quantization sensitive layers use 16 bits. It's much faster than into 16 quantization. We're using it in ESP-PPQ. Make sure that both sensitive layers and their adjacent layers are set to 16 bits. PPQ also provides us with advanced quantization methods, for example, weight equalization. You can find details about this method in this paper. It can help us just to deal with the range differences of potential quantization. In ESP detection, we recommend you to use this method for better accuracy. You need to adjust the parameters of weight equalization of yourself according to the model. Another one is horizontal layer split quantization. It also helps with the uneven tensor distributions in potential quantization. You can click the links to learn more about them if you are interested. After applying a quantization method to the model, how do we know if it works well? We provide two approaches for you. The first one is doing graph-wise and layer-wise analysis. You can get the output layers graph-wise error, and you can find the sensitive layers from layer-wise error analysis. The higher the noise-to-signal ratio, the larger the quantization error. The second one is running inference on a validation dataset. PPQ graph here is the quantized model. You can test its accuracy on the dataset. In ESP detection, we provide the evaluation script for you. So, what should we do if the quantization error is high from the analysis? Firstly, you can select a representative calibration dataset to better capture the tensor ranges. Secondly, you can optimize the quantization method, such as using mixed precision quantization weight equalization or a horizontal layer split quantization. If all these methods still cannot meet your requirement, please try QAT, knowledge distillation of supervised training. Finally, you can modify the model inference logic as we did, which can help reduce quantization error and accelerate model inference. Once we have a good quantized model, we can deploy it on our chips. To do that, you will need a few things first. For hardware, you need a development board, ESP32S3i, ESP32P4, EV function board is recommended. You'll also need a USB cable and a PC which runs Linux for development. On the software side, you need to clone the latest ESP detection repo and install the right ESP-IDF. If you want to capture the picture with the camera and run inference on the board, you will also need ESP hoop with the camera and display. Next, we can load the model. Here, we support 3 loading methods: loading from our data, loading from flash partition, and loading from SD card. Note that our data belongs to the application partition. With the code changes, the model must be refreshed. For large models, the application partition must be set bigger. Flash partition do not require refreshing. Copying from SD card takes longer. CC copy the model to PS RAM of internal RAM. So the 3 methods have different usages. If you want to start quickly and easily, use the default method, loading from flash out data. If you want to reduce flash time, use flash partition. If your flash is tight, use SD card. It also supports switch model and get online model. Note that there is a parameter called param copy for our data and flash partition loading. By default, it's true. It will copy the weights to PS RAM of internal RAM, which will slightly slow down the inference. If you want to speed up model inference, set it to false. Well, you need to check the model inference on board, whether the model inference on board is correct after you deploy it. In other words, whether it produces the same results as on the PC. When exporting the ESP-DL file, You need to include the test input and output and use the ESP error check function. If it works correctly on both, please export the ESP-DO model again and without test input and output so that you can reduce the model size. Otherwise, you can debug it with the generated info file. The info file contains the model structure, operator fusion information, quantized weights, you can see from here, and corresponding exponents. You can check whether there is overflow or underflow of the quantized values, whether the scale is normal. You can calculate the scale in this way. What's more, you can use techniques like binary search to find the layers where the error happens. Once the model runs correctly, you can check the memory usage with the provided function. For example, in CAD detection, it has 360 KB parameters. You can see the total memory usage here. You can also check the latency of each layer in the model with the offered function. By default, as you can see from this screenshot, it is ordered according to the model's structure. But if you want it to be sorted by latency, set the parameter to true. This information can be used for designing a lightweight model. In addition, if you set this variable to 1, it will print the latency of pre-processing, model inference, and post-processing. During inference, this is the result of CAD detection. Well, if the final result is wrong, check whether there is an issue with your pre-processing or post-processing on board, such as the reset method of the normalization. Now, we have completed the workflow. ESP-Detection also provides all-in-one operation for you. You can set the class name, pre-trained model path, dataset image size, target chip, calibration dataset, model name, and test image to generate an ESP-DO example. Then you can run the model with the comments. Now let's see some examples. Here we have cat detection, dog detection, and hand detection running with ESP-WHO. We capture the picture and then run it in real time. As you can see from the video, once a target is detected, it will show the corresponding bounding box. Okay, next, we will reduce the model layers to minimize the quantized model loss and improve FPS while keeping the accuracy. And we will develop a new lightweight model based on YOLO26. Additionally, we will optimize and release a dataset generation pipeline so that you can create your own dataset quickly. Well, now in summary, we introduced the ESP-Detection to you. It provides a complete lightweight detection pipeline for ESP32 chips, including model training, export, quantization, and deployment. We also introduced related work by our team, ESP-DO, ESP-WHO, and ESP-PPQ. All of these are open source on GitHub with detailed usage tutorials. If you have any questions, please feel free to open an issue. Our developers will respond quickly. Thank you.
That was really impressive demonstration from Wenjing. It still amazes me how much object detection you can run on such a small hardware. ESP chips keep proving they can do more than anyone expects.
Totally agree, Annie. And now we are moving from recognition to capturing the world around us. audio, video, and everything in between.
Our next speaker is Tian Haibo, who will introduce ESP Capture, a framework designed to make building audio and video capture system not only powerful, but genuinely easy.
With ESP Capture, developers can build applications like smart doorbell, dash cameras, live streamers, voice assistant, or even AJ analyzers, all using single unified API across multiple ESP32 platforms.
In this talk, Haibo will walk through the background context, the framework architecture, and the key components, capture sources, processing pipelines, automatic capability negotiation, and all the customization options available.
If you are working on anything that needs to see or hear the world, or if you just want to simplify your current capture pipelines, this is the session you won't want to miss.
Let's welcome Tian Haibo. The stage is yours.
Hello everyone, today I will talking about introduction of ESP capture, building flexible scale audio video capture system with ease. First of all, let me introduce myself. My name is Tian Haibo and I'm working in Espressif multimedia team. My main job including design and maintain such things like media framework, media protocols, and also I develop some media solutions. Let me go through the overall content. First of all, I will talking about some background on ESP capture. Then I will talk about the overall architecture of ESP capture. Then I will introduce each components of ESP capture in details. Afterwards, I will talking about the smart core of ESP capture, which means the building once and run everywhere capability of negotiation and so on. Finally, I will give a summary and provide some example link. Background. When we're talking about IoT, there are many related things. Like people, when with the eyes we can see, with ears we can hear. But how can IoT do this? We already know that IoT devices have some sensors to sensor environment like temperature, motion, and light. But to understand in the real world, they also need vision and hearing. Meanwhile, developers may struggle to combine camera and macro data easily. They may be redoing things a lot, like building media pipelines, do synchronization and encoding related things. That's what ESP capture comes with. It is used to turn scattered audio and video handling into one clean and flexible system. First of all, we see the overview of ESP capture, and the following its features and highlights. ESP capture provides a unified API for any ESP platform. Another thing is that it provides on-handy camera and codec support. Also, it supports auto pipeline generation through ESP-GMF, which we have new developed. ESP capture also supports automatic audio and video synchronization. Another highlight is that ESP capture supports multiple paths. It means it supports streaming while display at the same time. Also, it is quite easy to portable to another platform or ESP service, both hardware and software. Like we may support hardware encoding and software encoding. But with the CAPS support, we can just use one software, then most things will adapt automatically. We also support built-in encoders and maskers. We support encoding like H.264 JPEG, containers like MP4, FLV, and MPEG-TS. Also, ESP capture also support overlay. You can overlay like text. Most often, we can max timestamp into the video easily. Also, ESP capture support one-shot mode and streaming mode. It is used like to capture one image and stream the video. Finally, ESP capture also support customization. It supports many customization methods in different degree. Here is the difference of ESP capture and existing solutions. For audio and video integration, traditional approach may be used separate drivers, but ESP capture provides a unified API. For synchronization, traditional method may handle manually. Also, for the platform adaptation, traditional method may be use hardware specified code, means maybe it need add many macros to separate code. With ESP capture, we has abstract the source support into interface. It is to easily define new interfaces to adapt a new platform. Also for the media process pipeline building, typical ways may use manually, but ESP capture use auto-generated pipeline. Another point is ESP capture support multiple output. Traditional approach may need many coding and adaptation if changed a lot. Another point is customization. ESP capture support many customization through registration. This is what ESP capture can build. Scenarios like voice assistance, maybe use auto echo cancellation and provide noise-free background capture. Video recording means we can support recording encoded H.264 video and maxed into MP4 container and sell to local storage. Live streamer, we support live stream output of both audio and video. Also, it provides synchronization. AR vision and audio, we can provide AR-ready audio with pre-processing and combinations. It means we also provide some like WebRTC via AR vision. Here we show architecture in a dependency view. In general, ESP capture is divided into two parts: capture source and capture processing. Capture source is used to get raw audio and video. Capture processing is used to process the data captured from the source and through processing and send to the user finally. Here we can see the capture source with dependency on ESP codec device, which supports read data from the codec. ESP-32 camera, it can use to read data from DVP cameras. ESP video, the next generations of the camera support, it supports a variety of devices like USB, DVP, and MIPI. USB, UAC, or UVC, we can use it to capture USB media. For capture processing, we generally use ESP-GMF, including GMF video and GMF audio. It supports encoding and meanwhile some general audio and video processors. It underlies the modules ESP audio codec, ESP video codec, and the ESP audio effect, ESP video effect. Another thing is ESP-SR. It is the FE audio front end that support auto echo cancellation and other AI effect audio. ESP-MUX, it is used to the MUX audio and video together into containers. Following is the core building blocks of ESP capture. It consists of capture source, which get raw data from device, process path pipelines, including some converters, filters, and encodings. Capture sync. Capture sync is used to align audio and video timings and provide timestamp for them. MUX. For MUX is optional, means user can use it when needed. It is used to combine streamings into containers. Capture sync. It defines the use request output. We see the diagram that media data is captured from source, processed through the pipelines. Then it is fed to a shared buffer that used by capture MUX and audio video sync. It finally outputs through the sync. User can fetch from sync easily. Components. First of all, I will introduce capture source. Capture source is used to get audio and video raw data. Audio source. We abstract audio source through interface, audio source interface. And we support some built-in interface, which are audio device source. It is used to read PCM data from audio codec via ESP codec device. AEC source. It is also read data from ESP codec device, but it is pre-processed by ESP-SR, which provide auto echo cancellation, noise suppression, and other AI pre-processing like VAD detection. Video source. Video source is abstract as video source interface, and we support built-in interfaces like DVP source. It reads the video data from ESP32 camera. Only support the DVP camera. V4L2 source. It reads video data from ESP video stack. Currently, it supports DVP, UVC, and MIPI cameras. It is quite too easy to use at the user part. See the following code, user just need to do configuration. Then he can go to the source. Capture path. Capture path is the processor to get user design format. And we provide default path builder. It provides auto process pipeline generation. For general use, it doesn't need user involvement. It is all built automatically. User just need to call API ESP capture open, and the code size can be scalable. So menu configuration, like maybe we only support audio or only support video. Then we can disable audio or video to set the binary size. There is also an advanced path builder, means user can manually build the pipeline. User can call API ESP capture advanced or open. And we also provide some template pipeline builder that can use to build menu pipelines. For the general audio and video process, we can see in the diagram. For audio processing, we support auto level control, resample, sonic. Sonic is used to adjust the audio speed, bit convert, channel convert, equalization, and encodings. For video processing, we support color convert, scale, crop, rotate, the FPS conversion, overlay, and video encoding. Capture sync. Capture sync is just a logical unit that combine audio, video, and max all together, so users can get it from one unified API. Each sync gets data from the process pipeline. It provides a unified API to fetch the sync data. Most of the data is shared by point to avoid unnecessary copy. Also, multiple syncs are supported. It can run simultaneously. For multiple sync support, the source data is also shared. Auto process pipeline building is auto-finished for each sync, and it supports config and customize. Currently, when you use the default pipeline builder, it only supports one source to multiple syncs. But it's possible through manual pipeline builder. But it is a little complex. It need detailed negotiation. In the diagram, we can support that we have one capture source and multiple capture sync. One sync is used to do living stream. It output OPS audio and H.264 for video. Another sync, it captured RGB 5.6 file and used to display directly. Capture sync and max. Capture sync is used to align timestamp and generate presentation timestamp. It also is used to extract LPS control, like maybe the camera input is 15, but we just need 10 frame rate per second. For the capture sync, it is just a mode. User can configure it easily. Max. Max is used to max audio, video into containers. We have support multiple containers like MP4, TS, FLV, and WAV. We support storage the files into slices and named according users setting patterns. We also support to stream out via storage, means we can storage the max data into SD card, also stream out the max data like TS through network. And max is also used a unified API with audio and video. Here we can see the typical call sequence of the ESP capture. First of all, it needs to build up a capture system. For the audio capture example, it can use new audio device source to build up a source to read audio from codec directly. Then we can use the source to ESP capture open. Here we can get the capture system handle, then it can be used by the user. Capture sync setup. Capture sync setup is used to set up a sync to the designed format for user. Then you can call sync enable. We support one-shot mode and stream mode. User can toggle it dynamically. Finally, user can call capture start. Afterwards, user can call acquire frame to read audio, video, or max data. When the data is unused, the user can call release API to release it. Finally, when clear up, user can call ESP capture stop and ESP close. This is the all typical API for ESP capture. Here we will talk about the smart core of ESP capture. ESP capture support build once and use everywhere. It means we need only build the capture system once. Then we can use it in multiple applications. We can use a build-up capture handle for AI chat. It may only support audio-only format, while another app may want audio and video both for living stream. Another app may be use video record. It needs support max. So in the diagram, we can see the capture system build-up processes, just like as previously mentioned. You just need to firstly build up the capture source, then use the capture source build to capture system handle. Here you can see that the sync mode is used to do the synchronization. Auto negotiation can turn our solution to change platform and device easily. It abstracts devices difference into capabilities. Like some microphones may only support 8 kHz, but maybe the capture need 16 kHz. For some cameras, it may only support wave 422, but the display may need RGB 565. ESP capture will auto-negotiate the source capabilities. The auto-negotiation also including the pipeline building. We negotiate from the capture source to the capture sink. Then we insert the process element to finish the conversions. Also, we build up the processing unit through optimized. In the diagram, we can see that the input audio is 2-channel and output audio is 1 channel. Then the channel convert may be placed in the front. Other words, if the input is 1 channel and output is 2 channel, the channel convert may be placed in the end. After the pipeline build up, we also configure the full pipeline for each element. In sum, this auto negotiation maybe fit most of our need, but sometimes the negotiation maybe fail. Then we have an API called set fix caps for the source. It means fix the source to certain format. Then capture can auto-negotiate easily. For customization, we support customize in variety of degrees. First of all, we support a customized device through capture source interfaces. Then user can implement the interface to support new device easily. Also, we support customized process pipelines. Means user can customize the pipeline connection. So the ESP capture sync build pipelines. User can assign the connection of each element. Then the connection ship will auto-use one pipeline build. Also, user can configuration for the pipeline element on demand. User can get the element handle and do the configuration. Another point is user also support customize. So the template, we also provide a template realization for the pipelines. We also support customized for the dependencies modules. Like we support exist audio and video codec and Max. Also, users can call related module register API to replace the exist audio codec, video codec, and Max. Also, user can add their customized element. Use the ESP-GMF, he can achieve the customized process. Here is a summary for this presentation. ESP capture lets you build up your full audio and video capture system easily. ESP capture support multiple output, synchronization, maxing, and auto-adaptation. ESP capture also support modular, efficient, and scalable solution. All this is done in one unified framework. Finally, there is some example links. Include these links provide some examples for users to easily understanding ESP capture. We also carried some examples in the ESP capture example folders. There is also an example show pedestrian detection while streaming. We also can ask AI of our ESP-IDF docs. It can support auto capture code generations. That's all of my presentation. Thanks for your watching.
That was a great overview from Haibo. Every time I see ESP capture in action, I am reminded how much complexity it hides behind such an easy-to-use API. Audio and video pipelines have never looked so clean.
Totally agree. And now we are heading back into the world of Matter, but this time with focus on making development faster and simpler, which I think everyone appreciates.
Our next speaker is Chirag Attal, who will introduce how ESP-LowCode can streamline the entire process of building Matter-enabled products.
Chirag will show us how the platform helps developers create, secure, and deploy fully featured connected devices with far less friction, thanks to improved workflows and powerful integration tools.
So if you are working on a Matter device or planning to start one, this talk will show you how ESP-LowCode can take a lot of the heavy lifting off your shoulders.
Let's welcome Chirag Attal. Chirag, the stage is yours.
Hi, I'm Chirag from Espressif, a software engineer working on the ESP-LowCode and ESP-0code side. Let's just dive right into it and understand why we need low-code and what it is. So at Espressif, we have been trying to create a simpler development experience with all of our different products, starting with new IDEs. Then there is extensions for IDEs like VS Code, and then there is also the extreme end, which is zero code. A typical development experience looks something like this. You start with IDF, you maybe pick up some example, make your own changes. Then there is the entire editing, debugging, and optimizing cycle. And so this is a generic example, a generic product and a launch. Then on the other side, there is ESP-0code, which is the extreme other end, where you don't have to code anything. Espressif basically manages the entire thing for you. You basically just decide, try it out, and then launch a product. So this is, by the way, the fastest way to launch any product in the market. You should definitely try it out. With ESP-LowCode, it basically sits right in between both of these, where there is simplicity from zero code, and there is also the flexibility from the IDF experience. And the way we have designed it is that there is separation in a lot of things, which makes it easier for the application side to not interfere directly with the system side. It is like a split binary where there is a system firmware and there is an application firmware. There is memory separation, there is CPU separation. So whatever you do in the application side does not interfere directly with the system side, where there is communication with other devices, there is networking, there are other such stacks for the actual protocol. One such example of this split firmware which we have created is Matter, and that is the low code for Matter basically. Here the Matter logic and the Matter communication with other devices, the Matter setup, provisioning, commissioning, all of that is a part of the system firmware. And the application firmware handles the drivers, the actual business logic, which both of these are what is customized exactly by you, and you are the experts in that. Espressif handles the system firmware and you handle the application and the driver side of the firmware. And the good part here is that the system firmware is entirely managed and maintained also by Espressif. So you just need to focus on one part, which is your expertise. And the way we have simplified the developer experience for low code is you can directly get started from the browser itself. You don't need any host setup. It can run on Windows, Linux, Mac, whatever machine you have, and you can get started within just a few minutes. We'll just see how to go about it, and I'll give a quick walkthrough of what your first experience might look like. Now let's directly dive into the use case and see how easy it is to build with ESP-LowCode. You just go to ESP-LowCode Matter. This is the repository which we have specifically designed low-code for Matter. Here, Matter is the system firmware. The way to get started is just start a new code space. So you don't need to download the code locally. You can directly run it in the browser. This is on GitHub. It is now setting up a new code space for the repository. Once this is done, we'll see how the code structure looks and so on. And as I mentioned, Matter is the system firmware, and the application firmware is the actual product and the actual drivers. This hardly takes maybe 60 seconds, maybe 2 minutes, and that's it. Your system is ready. There is no setup locally required. The entire thing is running in the browser. And here I have connected my ESP-32C6 dev kit. The C6 dev kit has the LP core and the HP core, which we are using for low code. The HP core has the system firmware, and the LP core, which is entirely separated from the HP core, is where the application firmware runs. It is more like a bare metal coding environment, so there is no complexity of the systems involved. Now, while we were talking, the setup is ready and it is ready for us to use. So let's just see how can we use it. There are a number of buttons on the bottom. The way to get started is basically click all the buttons from left to right, and then it will automatically guide you through the process. So the first step is to select a product. This is what you will be building. For our use case, I'll just select a socket, which is like a power socket in Matter. So this is the app main, which is the entry point of the application. There is a easy setup and a loop kind of structure. The loop is here, it is just doing the feature updates. For example, one of the features is power, because this is a socket. So it will do the feature update. It will call the corresponding driver. So we have selected a product, then we just select a chip. ESP-LowCode already supports Matter over Thread as well as Matter over Wi-Fi. For our use case, we'll just select Matter over Wi-Fi and ESP-32C6, which I have already connected to my laptop. We just select the port for the C6 dev kit. It is detecting the port, verifying if things are correct or not. Next step is preparing the device. This is where the entire system firmware is flashed on the dev kit. It takes a while, but this only needs to be done once, because the system firmware, as we already know, is entirely separate from the application firmware. So even if you are iterating in the application, the system firmware does not change. And the app main, which you are seeing here, is the application firmware only. The system firmware is already a pre-built binary which Espressif maintains and provides. This is done. Next button is uploading the configuration. This is where your data model and other related things exist. So there is a configuration folder in your product. You can change this, you can edit this. Most of these are Matter specific things for the ESP-LowCode Matter project, because it is specifically for Matter. It is uploading, it is basically creating binaries which need to go on the device for the data model, and it uploads it on the device. Next is upload code. It is like a combination of different things. It is build, flash, and then also monitor. I'll just click the button. It is building the socket example. Then next is because the application binary is so small that it flashes in an instant, and directly you can see that the monitor has started. This is right now it is an entire working Matter application. It just took us maybe a few minutes to get started. You can open the QR code, you can scan the Matter ready QR code from here, and it will directly set up your device. Right now we'll skip the QR code commissioning, but we'll go through the edit, compile, debug cycle, which is one of the key points of low code. That this cycle ideally is what the developers spend their most of their time on, and with ESP low code we have tried to minimize that as much as possible. In the example, I just rebooted the device again. Now once the device reboots, I'll press the button on the dev kit. This is changing the state of the socket, as you can see. I notice a problem here that there are two different prints for the same thing. I'll just search this. I see that there are two prints in the driver. I'll go to one of them. This is the update, and this is where the state is set. So the second step is anyway going to happen. So maybe we'll just remove this one print and upload the code again. I'm just trying to show the quickness of the edit, compile, debug cycle that I just mentioned. It is automatically stopping the monitor. It is building, flashing, and again starting the monitor. So everything is happening just in a single button. And if there are errors, obviously it will pop out the errors and show them to us. And now when I am controlling the socket, it is just one print, which is, so basically our application code has been edited and flashed again on the device. And yeah, there are a few other commands. Some commands to help you in creating a new product itself. Maybe you have a vacuum cleaner. So you can select one of the other devices as a template. In this case, maybe I'll select a thermostat and enter the new name of my product. This created a vacuum cleaner product based on the thermostat product. There are temperature and other features in the thermostat, but you can obviously remove them and add your own vacuum cleaner features here. So yeah, this is pretty much it. Building Matter products and launching them to the market in a fast way, not the extreme fast way, which is ESP-0 but with this you get the flexibility and the less complexity. There is also the certification side of Matter. And in this case, in the low code case, since Espressif is maintaining the system firmware, we have a certain guarantee that the tasks and other things which are required for Matter, all of that are done well, and your product is basically certifiable. It should ideally seamlessly go through the certification process. There is still the application side of thing and the data model side of thing, but Espressif does have other services for that. So let's do this. We'll just quickly walk over the repository and the structure. So there are a few products which we have added by default, but obviously you can create your own, as we just saw. There are certain drivers. This is the low-level driver layer. Right now we support a few communication protocols, but that can be easily extended. There are other components which are required. There is system level, there is timers, there are the actual application level drivers, which includes light, a display, button, and so on. And in your example, there is the app main, which is basically just handling the different features and just forwarding them to the appropriate drivers. And the driver is where your kind of primary code lives, the application logic, the controlling different states and other things. So there is button callback, there is factory reset involved, because factory reset is usually triggered by the user. So it needs to stay in the application. The actual logic is still in the system, and that is why we are just sending an event to the system. So there is events and there is feature updates. These two are the primary communication mechanism between the system firmware and the application firmware. There is a quick driver initialization where we are, in this example, creating 3 types of drivers for our socket. And then there is the actual socket state handling and yeah. In most of the devices, there would ideally also be some indicators for the current state of the device. We have handled that in the event part, where there is a blinking LED pattern when the device is in setup mode, and that just the pattern just stops when the device is out of the setup mode. So that it is a clear indicator for the users of the device to know which state the device is in without looking at the logs, obviously. Yeah, that is a quick and small example, but it covers the entire matter part, even though the example and the actual application code is very small. That is the way ESP-LowCode is structured right now. The application is almost free of any matter-specific terms and matter-specific details that you might ideally not know or not want to know. Thank you, and I look forward for you to try out ESP-LowCode Matter. You can go on the GitHub. There is a discussion forum there. You can try it out and let's discuss there. Thank you.
Hello, everyone, and welcome back to the Q&A session. And now I'd like to invite Chirag and Gautam to this session. Hello, guys. How are you today?
Hello, we are good. How is the DevCon going?
It's going amazingly good. So we have now people from South America. We have like people from Brazil, people from Colombia, and so more people from Brazil, Germany as well. So we have many people here with us, and it's amazing to see how far we are going. Yeah, so Colombia again, Brazil, that's amazing.
Yeah,
all right, so yeah, and now you can say, where are you guys from?
Both of us are from India right now, streaming live, and everyone else in the world is watching. So good to know.
Great. All right, so let's start with some questions. So I'd like to know, how does ESP-LowCode Matter split responsibilities between system firmware and application firmware?
So as we mentioned multiple times in the talk also, the system firmware is completely managed and maintained by Espressif, and the application firmware is the only thing that the users have to think about. And by maintained, I mean even the for future OTA updates or for other things, the responsibility of the system firmware is completely on Espressif. We keep updating it to newer Matter versions. We keep updating and making the bug fixes and the security fixes in the system firmware. And the application is the small part, and the business logic and everything which the users actually are good at. Espressif is not good at, because Espressif does not know the business logic, and that is what we have left on the application side, and that is the only thing which we have left.
Okay, great. Okay, so thanks for adding this to your talk, and I like also to know, what are the key features in ESP-LowCode Matter that simplifies the build, flash, and debug cycle compared to using the full Matter SDK?
So basically, as we have seen in the code spaces, we have simplified buttons for all the predefined functions that we are going to do. For example, we have upload code, upload configuration. Upload configuration is basically for uploading the data model. So it's quite simplified there. And the application firmware size is also quite small. So you can build it fast, and you can debug and flash it faster. And moreover, if you see that there is a firmware separation, there is a firmware as well as CPU separation between the application and system firmware. So they both do not interfere with each other. So the debugging becomes much easier in that case, as well as the system firmware provided by Espressif. It has all the well-defined functionalities and events. So the user has to just focus on implementing their own business logic. They do not have to focus on implementing the matter stack itself. So that's a very simplified.
Yeah, that makes very easy to create a new matter device.
Yeah.
Yeah, and talking about like creating a new product, could you share best practices or examples for customizing the matter data model?
Yeah, so even right now, the low-code repository has a few different examples at different levels. For example, light bulb or a socket might be a basic example, a common device type. Then the next level for that might be sensors, and maybe a step ahead of that might be things like thermostat, air conditioners, and bigger appliances. So we already have examples at least for all of these. Then to get started, it might just be to pick some example, try it out, edit so in the configuration part, there is a data model section. You can just open the Zap tool provided by Matter SDK and directly edit your data model. You can just add the endpoints and other things from there and quickly try it with the low code platform.
Oh, I see.
think, yeah.
Yeah, and we have a question from Darian. Are the system firmware and app firmware able to run on the same core?
So right now the structure is a split core. So on C6, there is a main core and there is also a low power core. The way we have structured it is that the system firmware runs on the main core and the application firmware, which is a smaller firmware, runs on the low power core. So the application firmware's code also does not have things like free RTOS and other things. It is more of a bare metal application.
Okay, thank you. And one more question here. How does ESP-LowCode matter differ from ESP-0code?
Yeah. So zero code is basically zero code actually has a predefined business logic in its firmware. So in zero code, basically you can go to a website and use the product config to define your own data model. And in that case, if you want, let's assume you want to implement your own personal custom business logic. So in that case, the zero code does not provide that functionality. You have to move to the ESP-LowCode, and in ESP-LowCode, you can write your own application. It also provides the same leisure as ESP-0code, where we have the pre-built firmware as well. And in ESP-LowCode, you have system firmware, which is the same thing we are providing in the zero code as well. But in this case, you can just write your own application logic now.
To add to this, so ESP-LowCode basically fits in between ESP-Matter SDK and ESP-0code SDK. In ESP-Matter, you have the full flexibility, but you also have to take care about the Matter SDK and the Matter protocol side of things. In ESP-0code, you don't write any code. You just go to the website, select some drop downs and configure your product and immediately try it and test it, and you can launch it very quickly. Espressif maintains all the code and provides updates for all the codes. And ESP-LowCode now sits in between both of these, where Espressif manages a part of the code, which is the system firmware, and you basically are doing just the application firmware. So there is a lot of flexibility in low code, but all the complexity is kind of hidden in the system firmware.
Okay, thank you. And from the same person, from Fabio Embarcados, how does ESP-LowCode Matter simplify the Matter certification process? This might be a very interesting question for many people.
Yeah, so there are maybe a few parts to the Matter certification. In ESP-0code, because Espressif is managing the firmware, the entire thing is, the certification responsibility is also kind of on Espressif. In ESP-LowCode, there are two parts. So one is the system firmware and the Matter protocol part of the certification. And for the protocol part, Espressif, it is the responsibility of Espressif to be to make sure that the things are correct. We run a lot of tests on our side to make sure that happens correctly. But the application can still make the certification cause certification issues. So that part is still a responsibility of the customer or of the product designer. In addition to this, there is also other modes of certification in which they are trying to simplify the it is more of like a platform kind of thing where low code might act as a platform and there is something else built on top of it. So we'll see how this goes whenever these more things are being worked on for matter certification.
Great. Okay, so thank you very much for bringing this topic to the DevCon 25 and as well for joining us live for this Q&A session.
Yep, thank you.
Thank you.
Thank you. So see you in the next Q&A session.
Chirag really showed us how ESP-LowCode can take the complexity out of building Matter products. It's pretty amazing to see how quickly you can go from concept to a fully working device now.
Absolutely. And speaking of building things efficiently, our next session is all about multimedia, audio, video, AI, and how Espressif is bringing it all together in unified way.
We are excited to welcome Jason, who will introduce the latest updates in ESP-GMF version 1.0 and ESP-ADF version 3.0.
Jason will explain how ESP-GMF and ESP-ADF relate to each other and how they work together to form unified extensible multimedia solution for ESP platforms.
This session will explore the core components of ESP-GMF, including audio, video, and AI media processing, and how all of those integrate seamlessly with ADF.
He'll also highlight the key enhancements in ESP-ADF, such as optimized architecture and increased flexibility, enabling developers to build more efficient, real-time, and scalable multimedia applications.
If you're working on anything that involves sound, video, and AR-driven media pipelines, you will definitely want to catch this session.
So let's welcome Jason. Jason, the stage is yours.
Hello, everyone. My name is Mao Jianxin, and you can also call me Jason. I'm the audio solution manager at Espressif Systems. I'm very glad to share my topic with you today. Before we get started, let me briefly introduce our team. Our team focuses on research and development in audio, video, and image algorithm, as well as multimedia transmission protocols. We also design multimedia software frameworks such as ESP-ADF and ESP-GMF, and integrate AI technologies to build solutions for smartphones, children's education, home security, and robot voice systems. Today, I will be sharing my presentation from 4 aspects: ADF and GMF architecture, ESP multimedia core, ESP-GMF 1.0, and ESP-ADF 3.0. I will start to introduce the structure of ADF and GMF, as well as the relationship between them. Currently, most of the GMF 1.0 components have been completed, and the new features of the ADF 3.0 are under development. The GMF is a core framework designed to handle audio, video, and other types of stream data. The ADF 3.0 now stands for Advanced Development Framework for Applications. It provides a wide range of functional components for building real products designed from an application level perspective rather than a low-level technology one. The dialog on the right shows the structure of 4 of our multimedia repertories. The yellow area represents the ESP multimedia core, which provides the basic API and is located in the ESP-ADF libels repertoire. The purple area is the ESP-GMF repertoire, which includes various GMF-based components such as elements and audio players. The blue area is the ESP-ADF repertoire, which contains service components and other modules commonly used in the application projects. From a functionally hierarchy perspective, the components of ADF and GMF are divided into 3 levels: base level, mid level, and high level. At the base level, the GMF repertoire provided fundamental element components, including GMF AI audio, GMF video, GMF audio, GMF IO, and GMF MISC. Those elements from the building blocks of pipelines and can also run independently as possible units. The middle level consists of functional components built on top of those elements, offering ready-to-use interface such as ESP capture and ESP audio sample player. Finally, the high level including service components that provides application APIs. Those services are designed to support multi-object and are ideal for direct integration into real-world applications. Now, let's move to the lowest level library, ESP Multimedia Core. The ESP Multimedia Core is a collection of audio and video algorithm library and multimedia transmission protocols developed by Espressif. It includes commonly used audio and video codec effects processing algorithm, network transmission protocols, and container marking demarcation tools. Those algorithms greatly expand what Espressif chip can do, allowing them to handle complex real-time multimedia task pre-autos. With the multimedia core, developers can quickly build smart home device, AI-based audio and video solutions, and stream application with the IDF environment. It can also be integrated into other environments such as Arduino and MicroPython. The two components in the gray area, ESP MIDI and ESP extractor, are currently under internal review and will be released soon. Now, I will introduce each related component one by one. The first one is ESP audio codec. A core component is our audio framework. The ESP audio codec latest version is 2.3.0. It is optimized for Espressif hardware, providing frame-level encoder, decoder, and sample decoder interface for real-time, memory-efficient audio process. Its unified API makes it easy to integrate and manage multi-codec across applications. It supports encoder like AAC, AMR, ADPCM, OPS, LC3, and decoder such as MP3, AAC, SBC, LC3, along with popular container like Wave, M4A, and TS. Those capabilities allow flexible use in music player, voice call, high-quality recording, streaming, and voice recognition. The 2.4 is coming soon with more enhancement. For detail, see the components link below. Let me introduce ESP audio effects designed to make professional audio process simple and effects for the embedded device. The latest version is 1.1. It provides a complete audio toolkit for core effects like audio level control and multi-band equalization to utilities such as audio mixing, sample rate conversion, fade in, fade out, and even bit depth and channel format conversion. Whether you are building smart speaker, headphones, or recording device, these components gives you a solid audio foundation. Version 1.2 is coming soon and will add some new features. You will follow the updates through the components link below. This is ESP image effects, a powerful component that bring image effects process to embedded devices. It offers a complete toolkit from color conversion and rotation to scaling and cropping, making it ideal for smart camera, industry vision, and IoT application. With hardware acceleration and algorithm improvements, it can process image in the real time, even on device with limited resource. On ESP32P4, it handles Full HD color conversion at 18 FPS and image scaling at 44 FPS. Version 1.0.1 is available now. For detail, see the components link below. This is ESP video codec, which provides a complete set of video codec interface for embedded devices. It offers a unified API for all codec operation, optimized performance through hardware acceleration and memory management, and flexible codec support across ESP32 chips from S3 to P4. These components enable real-time video application, including recording, playback, video call, and AI vision system. The current version is 0.5.3 is available now. For details, see the components link below. We have released ESP Media Protocol, a collection of multimedia transmission protocols. It supports STIP, RTSP, RTMP, MRM, and UPnP, and can be used for real-time communication, live stream, and multi-room audio. It offers no resource usage, under 20 kilobytes memory on ESP32 S3. Wide protocol coverage from voice call to video surveillance and a unified interface for easy integration. Ideal for smartphone and media application, including home audio, video multimedia, live stream, and voice call. For details, see the components link below. Next, let me introduce the new components included in GMF 1.0. ESP-GMF 1.0 provides two layers of APIs, basic level elements and mid-level functions. The base level elements are built on top of the multimedia core library and can be used independently or combined into pipelines, making them ideal for advanced development or in-depth customization. For most users, the mid-level function offer high-level functions components that simply come task. For example, ESP capture handles audio and video input. ESP audio render manages audio output. The ESP player provides the playback and the control for both audio and video. Those mid-level components are built on the base level in elements and leverage the GMF framework, making development faster, easier, and more efficient. Here, I will introduce some new components. First one is GMF video components. It offers a comprehensive set of video process elements, including encoding, decoding, peaks processing, frame rate conversion, and overlay mixing. The table below summarized the support state of those functions on our chips. Note that the peaks processing accelerate supported only on the P4. GMF AI audio component provides a set of commonly used AI audio algorithms, such as AEC, VAD, weak word detection, and command word recognition. GMF loader component is a utility package that offers convenience API for GMF application development. GMF AI utilities is a helper component that allows users to easily customize their GMF pool through menu configure. Let me introduce you to ESP Audio Render, a high-level audio component for GMF. It observed a complex problem simply: how to mix and process multiple audio streams efficiently. It can mix multiple PCM audio streams together in real time. It applies operation audio process like volume adjustment, speed change, or equalization, both before and after mixing. It handles all the conversation for you, automatically adapting simple rate and format, and it gives you real-time control over playback with pause, resume, and flash commands. So if you are building an application that needs to manage more than one audio source, ESP Audio Render simply the entire post-decoding workflow. Let me introduce ESP Board Manager, a component that makes board-level hardware setup for ESP chips faster and application development simpler. The idea is simple. You no longer need to write repetitive code to configure I2S, SPI, or GPIO. You just describe your board in a clear YAML file, and the board manager automatically generates all the initialized code. With this component, all hardware configurations are centralized. Code reuse is higher and stability is improved. All boards used a unified API, keeping application code clean. So switch to a different board doesn't require change in the application layer. It also automatically handles components dependencies, allow easy switching between board configuration, and adding new prefers and devices straightforward. Overall, use the ESP Board Manager to adapt a new board or change hardware configuration takes only a fraction of the time compared to traditional methods. Version 0.4.1 is now available. Please see the components link in the details. Now, let me introduce the feature of the ADF 3.0. ADF 3.0 directly leverages the features and components provided by GMF to build higher-level service APIs. As shown in the figure below, those are some commonly used service components. Key features and capability of service includes high-level APIs with independent functionality, thread-safe operations, capability discovery and query support, MCP support, low power management, minimal resource overhead. Let's use the multimedia player service as an example to explain how our service is used and how components interact. App 1 wants to play music, so it sends a request to the media player service. At the same time, App 2 wants to play a ringtone, and it also sends a request to the media player service. The media player service receives the requests and decided how to handle them based on its configuration. For example, whether to mix the audio or switch between streams. Depending on the handling method, the media player service calls different components. For instance, if it needs to mix multiple audio channels, it will use audio render to perform the multi-channel mixing. That's all. The above content is my presentation. Thanks for watching. If you have any questions, please feel free to contact us through GitHub or our sales team.
That was a packed session from Jason. Lots of new possibilities with ESP-GMF and ESP-ADF. I'm pretty sure a few projects ideas just appeared in a lot of people's head right now.
I guess same here. And before we deep dive into our next topic, this is good moment to hit pause button for a bit.
We're going to take a 15 minutes break now. Perfect time to grab a coffee, stretch, answer a couple of emails, and just let all new information sink in.
Don't wander too far though. We have got more great talks coming up right after the break.
See you here in 15 minutes.
Stay tuned.
Welcome back, everyone. Hope that 15 minutes break gave you a moment to recharge. We've got great content lined up for the rest of the day.
And now we are shifting gears a bit. Our next session brings in a fresh outside perspective, straight from one of the ideas many developers know and love.
We're excited to welcome Ilya Motorny, a developer at JetBrains and one of the people behind CLion, their PyFlow C++ IDE.
Ilya is going to show how you can develop ESP32 firmware using ESP-IDF directly inside CLion. He'll cover everything from starting a new project to version control workflows and even AI-assisted code completion.
He'll also demonstrate how CLion simplifies debugging and streamlines the development experience, making embedded programming feel much more intuitive, especially for newcomers and anyone looking to optimize their workflow.
So, if you have been curious about using CLion with ESP32 or you are looking for smoother development environment, this is perfect session for you.
Let's give a warm welcome to our external speaker, Ilya Motorny.
Hello, my name is Ilya Motorny. I work on the CLion team at JetBrains. CLion is a cross-platform IDE from JetBrains, very similar to PyCharm or Android Studio, but focused on C and C++ languages. Today, I'm going to talk about how to use it for embedded development with ESP32 chips. The IDE helps you to be productive with its deep language analysis, with code assistance, special features, for embedded debug and AI capabilities. Today I will demonstrate everything on my Windows laptop, but note that CLion and ESP-IDF, they are both cross-platform, and Linux and macOS experience will be the same. I have ESP-IDF framework master version, which is going to be 6.0 installed on my computer, and CLion version 2025.2. Also, I will be using this S3 box device from Espressif. It is based on ESP32 S3 chip and is equipped with touchscreen with couple of microphones, SD card and external connectors. And it could be a base, for instance, for an IoT network. Let's start with a simple Hello World project for my S3 box. First of all, I need to change settings of my CLion to be able to work with ESP-IDF projects. I open CLion settings. Since I'm going to debug my firmware, I'll go to advanced settings and enable debug service, which is relatively new feature for the CLion. Apply. And now I created tool chain for my ESP-IDF. I create a new tool chain of type min.gv. On Linux or macOS it would be system type. Give it a reasonable name. And add an environment script from my ESP-IDF installation. Yeah, here we are. Master. Open. Save the settings. Now my CLion is ready to work with ESP-IDF projects. Let's create an empty project. I open IDF terminal, change to my desired folder, and create an empty project. Yes, done. switch back to CLion and open the project. Now I need to make proper settings in my project. First of all, I select a new toolchain, define my target MCU, ESP32S3 for my board, and a standard build directory. Now CMake is opening, parsing, and generating the build for my project, and while it happens, I will initialize Git repository in my project. I always do that because Git, even the project is not going to be published anywhere, Git helps me to keep track of my progress and save milestones to commits. First of all, I go to settings again and disable automatically detected Git repositories, because the framework is included into project, and the framework is set of Git repositories, and I don't want to track them. And I go to settings, version control, directory mappings, remove whatever is detected, and disable automatic directory mapping. Now I go to version control menu, and create a new repository for my project. Next step is to add a gitignore file. Since we have Git repository already initialized in the project, all the new files are suggested to add to the commit set. I include my build project, build folder to gitignore, and SDK config file, and SDK config.old file. I don't want those files to be kept in the Git. Now we are ready to make our first commit. Here in the commit window, I see all the files. Yes, I want to include them to my very first commit. Select everything, and then I'm a lazy guy, and I ask my AI assistant to generate a commit message for me. Sounds about right. Let's make a commit. Yes, the very first commit is done. Let's go to the code and then add some functionality. We have an absolutely empty file here, and I want to add a hello world functionality first. I add an infinite loop, which is unusual construction for like normal C application, and CLion immediately reports me that there is warns me that there is an endless loop. I think this is fine for embedded application, and I just mark my main function as no return. The warning is gone. Fine. Let's add print. Now I need to add some delay. Include FreeRTOS. And add the actual delay. let it be 700 milliseconds. But we are writing an embedded software, so let's add some blinking functionality. I have a GPIO 47 in S3 box connected to the display backlight, and I want to blink it. But again, I am a lazy guy. I would prefer AI to do the job for me. So I press a Ctrl / and just prompt it to help me. Let's see what happens. We never trust to AI. Let's check if the code looks correct or not. Yeah, for me, it's acceptable. So let's accept. Now we are ready to compile and try our firmware on the actual board. I will start the compilation process and prepare running configurations while the firmware is being compiled. First of all, I have a bunch of run configurations automatically detected from my CMake structure, but they are actually not really convenient for working with ESP-32. I will make 3 new ones. So I find the major run configuration here, make a copy of it, name it all. This run configuration is going to compile and flash all parts of my application, including bootloader, partition table, application code, or whatever is going to be added to my project. As a target, I select flash, and then I will put my new run configuration to a dedicated folder named ESP. Here we are. Sometimes I don't need to flash all parts of my firmware to the chip, and just to make my work faster, I will make another copy of this configuration, name it up, and then replace the target to up flash. This run configuration will keep my bootloader and partition table untouched, and will just start faster. And the third configuration is just to restart my debug session without flashing anything. I make another copy, name it debug, and remove build step. Run configurations are done. And since we have a ESP32S3 with debug probe on the chip, I want to debug my application, and I create a debug server for it. Name it ESP-IDF. There is very little settings to adjust. I will just add some longer delay. Now I'm ready to start my firmware on the actual device. So I select all, run configuration to have all parts of the application flashed, and just press debug button. So the screen started to blink. Firmware works, and here in the run window we can find the serial monitor running. I can, yes, let's clean it. Yes, hello world statements go. And here we have a debugger, and I can put a breakpoint somewhere. And all the debugger features are available for me. I can watch status of variables, and also I can watch peripherals of my chip. But I need to get an NSVD file for it. Fortunately, thanks to Espressif, they publish SVD files for all their chips. There is a special repository at Git. I find a suitable SVD and just download to my project. Back to CLion, load this SVD file. It's a huge amount of different peripheral registers, but I will watch only my GPIO responsible for blinking the screen. So I just enable out 1. That's enough for me. We see the content of out 1 register, and some bit is switched on there. That means my backlight is on. On the next loop, it's off. On, off. So now our firmware works, and we can make another commit to the repository. I go to my commit window, select all the files, and make another commit. Here in the Git window, the whole structure of repository could be shown, all the branches, all the commits and trees, and they're quite handy. Second example. Let's try more complicated application. This time I will use one of the standard S3 Espressif examples. It's not for my board, but for some very similar device, for box light, but I guess the application should be working for my S3 box as well. So here's a page of the example application at ESP registry, and there is a copy. There is a command to create the application out of the example. Copy the command, then I start my shell again, run that command, and the example is here. Back to CLion, and I will open that example. The same set of activities, select toolchain, set the target, build directory, CMake immediately starts to parse the project, but I will stop this process because I need to make some adjustments to the project configuration first. I go for my components and replace the board support library for light for box 3 and set the last version. Now we are ready to work with CMake. This time CMake parse will take much more time because it downloads the components from the registry. And I will make my Git repository again. create Git repository. Add git ignore. This time I will add more files here. Build directory. CMake finished its work, so let's compile the application. And while the application is coming, I will make my very first commit here. Slight change to the AI suggestion. Commit. The compilation still goes, and I will create the same run configurations as before. app. And the debug server. So the firmware is compiled, the project is ready. Let's start the application. I select the all and debug it. My firmware is being flashed to the chip. And the application is running. Let's check what happens in the console. Yes, the application looks running. This application listens to a sound with onboard microphones and shows the spectrum of the signal. Let's go to sources and stop at some interesting breakpoint. For instance, here. Now the execution stopped at the breakpoint, and I can check what happens inside my off-screen buffer. There is a variable for it. I need to convert it to a pointer. Here we are. And let's look at that as an image. I need to manually set the parameters. RGB 3 channels. Data is being pumped from the MCU memory. Let's select the proper image format. Yes, and we have a copy of our screen right here in the debugger. Now I disable breakpoints and let the application run for a while. And let's play some music to see the spectrum of it. That's enough. Let's see what happens in our screen buffer. The data is slowly pumping, and yes, now we see the spectrum of the song I've been running on my computer.
Hello, and we are back for another Q&A session. And for this session, I would like to invite Ilya. Hello, Ilya. How are you today? We might have some audio issue. Hello, Ilya. Okay, we might have an issue with his audio. Maybe he's not able to hear us. Let's see if we can fix that.
Hello?
Hello, can you hear me?
Yeah. Sorry, I was on
no problem. So first of all, thank you very much for your talk and for being part of Espressif DevCon25. This is probably your first time here, and we are very happy to have you this year.
Yeah, thanks for the opportunity.
Yeah, so we have some questions here, and let's start with how does CLion improves ESP-32 firmware development compared to other IDEs?
To do other ideas. Good question. So how do I answer, first of all? Do I just tell you and you type the answer? Okay.
Yes, you can just
improve. CLion, I think CLion is the best. I think CLion has a language analysis best in class. So it brings all the JetBrains experience in supporting different languages to C, C++ world. So we are generic IDE for C, C++, and we work with ESP-IDF framework, but our main strength is the language support, which we bring to embedded development. So second question is more or less the same.
Yeah. So so do you see any limitations or challenges when using CLion with ESP-32? Maybe from your point of view.
We just started to support the framework, so we are working on it to improve it every day, and it's gonna be better now. But for now, it's like not really 100% stable. Also, not all the features work well. But on the other hand, well, it will be improved really soon.
And how do you see the adoption of CLion from ESP-32 users? Do you see like a number increasing? How do you see?
Honestly, I have no numbers at the moment, but we definitely try to make our best for not only ESP developers, but also for any kind of all kinds of embedded development. I believe that we grow in the market, and yes, since we are just started. I hope that the number grows, and after this conference, probably it will grow more.
Yeah, so it's a nice opportunity to invite people to try CLion with ESP32s. I think there are many benefits, and you already mentioned a couple of them during your presentation. So now, how people can get started with CLion? Where should people go and download and get started with?
Since like as previously CLion was known to be a paid product, but now it's free for non-commercial projects, and even for commercial projects there is a 1 month trial period. So just go and download this CLion, and then install ESP-IDF framework and follow the documentation or this video. That's the easiest start. Yeah. Better to start with newest chips with debugger on board, with S2, S3, C3. Yeah.
And now that it's free for use for no commercial projects, there are a lot of opportunities for makers and the community to try. So that's awesome.
Yes. We decided to make it free for non-commercial, and we got a huge number of new users recently after that turn.
All right. Okay, so again, I'd like to thank you for preparing the talk and for joining us for this Q&A and for being part for the first time at Espressif DevCon. So thank you very much. So see you in the next live Q&A. Thank you very much.
Ilya's session really shows how much smoother firmware development can feel when the tools do half the heavy lifting for you. I think a lot of people are going to give CLion a try after this one.
Definitely. And now we are jumping into the topic that everyone encounters sooner or later, whether you are building a battery-powered device or high-speed peripheral. It's USB Type-C.
Our next speaker is one of our own, Tomasz Rezucha, who will guide us through how to fully harness the power of USB Type-C in ESP-based designs.
Tomasz will walk through the essentials, implementing reversible Type-C connectors, handling both power delivery as well as data transfer, and configuring ESP microcontrollers as either host or device for high-speed USB communication.
He'll also cover how to work with USB power delivery profiles to safely negotiate charging currents and how to integrate cost-effective Type-C components without sacrificing performance.
Whether you are building an IoT node that needs fast charging or custom peripheral that needs reliable high-throughput data, this session will give you practical techniques, reference schematics, and real firmware example.
So let's welcome Tomasz. Tomasz, the stage is yours.
Hello everyone and welcome to this USB Type-C talk. My name is Thomas. I work as a USB embedded engineer for 5 years in Espressif, and I will tell you what you can do with Type-C connector on ESP32 series of SoCs. So let's have a look at what is in front of us. The introduction to the Type-C connector will be very short because as of now, it is very well adopted. It is used in variety of devices, scaling from simple PC mouse to high throughput data transfers with DisplayPort and power delivery charging. But we will start with basics and have a look at new signals with stress on configuration channel, which every Type-C device must now implement. Following that, we will have a look at how it affects power and data roles, even with dual role ports. And lastly, we will have a look at what software support you can get on Espressif chips. With Type-C connector, you get reversible, compact, modern standard that is well adopted. If you need to transfer data or power, this connector might be the right choice. But complexity of the design rises compared to the previous connectors. Now, role of the port, that is whether it is host or device, cannot be easily determined by the connector type. Because with the USB-C cable, both host and device have the same receptacle. And don't forget that we can also have dual role ports that can act as both device and host. With the old set of connectors here on the right, the role is clear from the connector itself. For example, type A connector could be only connected to host port, which inherently avoided unsupported connections. On top of that, each side of the Type-C cable, we have a reversible connector, resulting in possible 4 combinations how the wires inside are connected. And this is still a very simplified description. So how do we detect what is on the other side of the cable and establish a valid connection? To answer this question, we must have a look at what is inside of the Type-C connector. In this picture, you can see 2 sets of 12 pins, totaling at 24 pins for a fully featured cable. The two sets are symmetrical, so A1 is symmetrical to B1 and others the same. So all the signals are doubled, and some, for example, power pins like V-bus will be here and here, and ground on the edges of the connector could be shorted in the cable and on the PCB. Moreover, not all cables must have all 24 pins inside or wires inside. For example, a simple USB 2.0, that is high-speed only cable, can have only the original signals implemented. The original meaning V-bus for power, then ground, and then D plus and D minus, and the same on the other side of the connector. Going forward, you can see that super speed differential pair that were introduced in USB 3.0. So here is one pair, second pair, and then of course symmetrical for the reversible connector. But this is not relevant for ESP applications. And finally, we have 2 groups that are entirely new and exclusive to Type-C interface. It is the SBU called sideband use. This is not really important for the basics, but for completeness, it is used, for example, for audio accessory mode or for DisplayPort modes. But the most important for us are the configuration channel signals, shortened as CC1 and CC2. Let's have a closer look at them. The CC1 and CC2 form a configuration channel. It is the most important change for USB 2.0 applications because every Type-C port must implement the CC channel signaling. Now, why do we even need it? To understand better, we must have a look at the original USB 2.0 standard that did not think too much about dual role devices, and it gave only limited features to devices that used USB only for charging. On the other hand, Type-C connector can be used for devices, host, dual role ports, and the power path is less coupled with data path. For example, without Type-C, we cannot have power sourcing device or power sinking host, something like a USB-C docking station that is also charging your laptop. Of course, there were attempts to deal with these shortcomings in the past. There was a battery charging supplement that allowed higher charging current, and also the on-the-go standard that introduced the micro AB connector that allowed dual role ports. This, however, resulted in a large number of different connectors, adapters, and also vendor-specific charging solutions, which complicated the USB ecosystem even more. Fortunately, the on-the-go standard is now deprecated and superseded by Type-C. So every new dual role port must implement Type-C connector. Best examples is our smartphones. They actually act as device when connected to host PC, and they act as host when connected, for example, to a USB flash disk. So back to the original question, how do we detect type of the port on the other end of the cable, and why do we need dedicated pins for it? Now, every Type-C downstream facing port must pull up each of its CC lines. So this is the downstream facing port. These are the CC lines, and each must be pulled up. On the right side, we have a sync port, and it must pull down the CC lines. Also notice that only one CC line is connected through the cable. The other is either entirely disconnected or it is used for some alternative features that we can discuss later. This allows us to detect cable orientation, because the cable can connect from CC1 to CC2, or for CC2 to CC1, or also CC2 to CC2, but always only once. And this way we can detect orientation of the cable. And this is very important for USB 3.0 and later versions signaling. So how it works? Both ports must monitor voltage levels on their CC pins. So the CC pins are here. Once the ports are connected through a cable, so this is the cable, the resistors form a voltage divider. The source port detects attachment when the CC pin is pulled low, and vice versa. The sync port detects attachment when CC pin is too high. After that, the source turns on VBus. This is another new thing in Type-C, because in Type-A connectors, VBus was always enabled. But in Type-C, it is disabled by default for every port. Now, why would we disable VBus by default? This solves the problem with connecting two sources with Type-C cable. In this case, both ports would try to source VBus, which could damage the DC-DC converters inside. So VBus is disabled by default and is only enabled after valid sync is attached. This resistive CC attachment detection also solves host-to-host and device-to-device connection, because if you connect two sync ports with pull-down, neither of the ports detect attachment and both ports remain in an attached state. Okay, so now we understand what configuration channel is. Next, let's have a look at how can it define power roles and what options does it provide. We will go through requirements for Type-C ports from lowest power to highest and see boundaries where the complexity rises. The first boundary is 2.5 watts. This is the maximum power in USB 2.0 specification. For USB 3.0, you can get as much as 4.5, but no Espressif chip supports USB 3.0, so for our applications, 2.5 is the maximum. And it is also default for Type-C ports. Here the implementation is very easy. If you transition your old USB design to Type-C, you just swap the connector for the new one and add the required pull-up or pull-down resistors. However, if you're designing a source USB host, you must also add the VBus switch to be fully compliant. So given this constraint, it might be easier to use the good old USB-A connector for host-only applications. Of course, if you do not need the smaller footprint or fast charging that the Type-C offers. Which brings us to Type-C charging without power delivery. This stops at 15 watts. We still have 5-volt VBus, but the current can get as high as 3 amps. However, the complexity has not risen too much. Source still needs the VBus switch, but any Type-C capable will work just fine. The only added complexity on the sync side is that it must monitor voltage on the CC line to make sure that the source can provide the required power. So looking at the schematic that we had before, on the source side, we added pull-up resistor, but this can have different values, and different values map to different advertised maximum current. So there are 3 options: 0.5, this is the default, then 1.5 and 3 amps, each with different value of RP. Once the thing is attached, the resistors form a voltage divider, so this is just a simple resistor signal. On the other side of the cable, the sync must monitor the resulting voltage of the divider to know how much is the source offering, and it must not sync more, so it would not overload the source. In the real schematic, it's also very easy. This is the Type-C connector and 2 pull-down resistors, 1 on each CC line. So this is a sync device that uses default power. If the sync port needed more than the default, it must monitor voltages here on the divider, here and here. Of course, only one of the CC line is actually connected through the cable, so only one of these 2 provides a valid signal. If this is a source port, we must add a VBus switch that would enable us to turn the VBus on or off to be fully compliant. Above 15 watts, the complexity rises significantly. And that is the reason why many cheaper chargers stop at 15. And this is a 15-watt adapter for Type-C charging. So the next boundary is 60 watts, and the added complexity is power delivery. With power delivery implemented in both source and sync ports, the ports can negotiate a power delivery contract, and the voltage can be set as high as 20 watts. So if you want to reach this level, you must have a programmable DC-DC power source or adjustable power source. You must have a power delivery IC, because it is not possible to beat bank power delivery protocol in a compliant way. And finally, you must extend your firmware to actually negotiate the power. The power delivery communication uses biphase mark coding on the active CC line. So again, you can see that the other 2 pins are not connected through. But this is out of scope of this talk, so I will only tell you that the easiest way to achieve this is by adding a Type-C controller with power delivery to your design. Because implementing your own discrete power delivery PHY is not cost effective. Also notice that the maximum current is still capped at 3 amps. So we are 20 watts, 3 amps. Because above 3 amps, you need electronically marked cables, so-called E-cables. This is for electrical safety. The cable must be marked that it can handle currents above 3 amps. In practice, there is a small IC in the cable, and the source port must read it to make sure that the cable can handle the currents. E-marker's chip is usually pretty simple, can be only just on one of the plugs. But another thing is, as you can see in the picture on the very bottom right, some cables for high data throughput can also have signal conditioners inside in their plugs. Cables like this are usually included with Type-C monitors, where single USB-C cable carries power DisplayPort data on top of USB superspeed data. But this type of cable will be significantly thicker and also more expensive. So with power delivery and E-marked cables, you can get up to 100 watts. If you need more than 100, you enter extended power range territory with even more strict electrical requirements. Here, the complexity of the power path rises significantly. We won't go into any other details because from here it is more about power design than USB. But to sum up, here you can see the complexity boundaries. With Type-C, you can get 15 watts relatively easily and cheap. This is a great advantage. Above that, you will need external power delivery controller. Okay, so now we know something about power and data roles. Let's make a final step and put it all together in a dual role port. This is a picture from a USB Type-C specification. The document itself is pretty long, so you must find the chapters that interest you. Luckily, they are often full of nice diagrams that will help you understand it fast. For dual role ports, the Type-C connector is a must. The complexity rises in software and hardware as we need to both source and sink power, and we want to act as both USB host and device. In the picture, you can see the source port here connected to a dual role port on the right. Everything that we discussed, apart from power delivery, must be implemented. We have a V-bus power switch here and also another switch for sync. Only one CC line is connected through the cable. For simplicity, CC1 to CC1. And we can pull the CC lines both up and down based on the role we prefer. Actually, the dual role port must alternate between pull up and pull down, present itself as sync and source until valid attachment is detected. However, without power delivery, the power and data role must always match. For cases where you need sourcing device or syncing host, for example, as the USB-C docking station that we discussed, power delivery is a must. Okay, this is another screenshot from the specification. It shows a state machine for a dual role port that must be implemented. And if you have a bus powered device, most of the state machine must work even with that battery. What I'm trying to say here is that given the complexity and strict timing requirements, the best and cheapest solution is to use a dedicated Type-C controller integrated circuit. The Type-C controller will negotiate the power and data role even with dead battery. Remember that Type-C host will have its V-bus off by default and will turn it on only after a valid sync connection is attached. A block diagram can look like this. This is a picture from TI Type-C controller datasheet. So on one side, we have the Type-C connector, and the CC pins and also V-bus for sensing is connected directly to the controller. It's handled inside the controller. For source or dual role ports, we also must have the V-bus switch. And the USB data lines can be directly connected to ESP. Then we can also connect the GPIO and Espressif from the controller to our ESP32. Some Type-C controllers can be programmed through Espressif, some through GPIOs, some both. So some can even control the external V-bus power switch, which makes the design even smaller and simpler. And now software. In this final section, we will have a look at what software changes your design might require when you move to USB Type-C connector. First of all, let's have a look at the software stack for USB data on our chips. There are two separate stacks, one for host mode and one for device mode. They both need exclusive access to the underlying USB peripheral, so only one of them can run at a given time. For host mode, we use the USB host library. This is an in-house developed library. It was part of the ESP-IDF, but for ESP-IDF version 6.0, it was moved to a separate repository called ESP-USB, where all the other USB code is. For device mode, we use TinyUSB open source project that is ported to all Espressif USB-enabled targets. Together with the software stacks, we ship class drivers and examples for both host and device that will help you get started with your next USB project. The good news is that if you transition your design to a Type-C connector, there is no need to change anything in the software stacks. Changes are only required if you want to use some of the new features that Type-C offers. Let's have a closer look. First case is the simplest, because there is no change in software. If you have a USB device that syncs default power, there is no need to change. A slight change might be needed if you want to design a fully compliant USB source. In this case, you must add the aforementioned V-bus switch, which can be controlled by hardware or by software through a GPIO. However, still a trivial change. The second tier is Type-C charging up to 15 watts. That requires a sync to monitor the CC line. This can be done through an ADC in your microcontroller, which will need some software handling, or via a dedicated Type-C controller, which again requires software driver. This will take a little more work, but still pretty easy and cheap to implement. For dual role ports, the situation is getting more complex. As I said before, a dedicated Type-C controller is recommended, so again, you will need some software driver for it. And you must also switch between USB host and device stacks, as we saw in the slide before. Fortunately, the host and device stacks that we provide already support role swapping, so nothing too complicated. And finally, power delivery. There are many options. It can be done as source only, sync only, or any other combination that we discussed before. Here you must add software for the Type-C controller and also software that will handle the power delivery features. So here we can have a peek to our future software plans. This talk is pre-recorded, so some of the features might be already released by the time you are watching this. In the picture, you can see a snippet from software architecture. You can clearly see the software stacks. The blue one is device stack, and green is for host. Now, the first goal is to be able to switch between them. So another layer is introduced on top of it that can uninstall one and install another stack to be able to change the data role. So this is something like a role manager. But to get the source or sync attach events, we first need software for the Type-C controllers. So here another component is introduced that will handle it. Not to introduce more confusion, we took the naming from a Linux USB driver, so it's TCPM, short for Type-C Port Manager. This component abstracts away specific hardware implementations, so you can pick the controller IC from any vendor you like. Now, this port manager exposes two interfaces. The first one is only for Type-C controllers without power delivery. So we can detect attachment of sync or source, accessory modes. We can get sources, power options, and control VBus. The second interface is optional and extends the first one with power delivery protocol. So you as the user will just provide preferred role and capabilities or requirements for power path, and the software will negotiate the power contract and configure the rest. And even lower, you can see implementations of or drivers for specific ICs. For example, HUSB 320 does not support power delivery, so it implements only the Type-C interface, while FUSB 302 implements both interfaces. There are many others on the market, and we can implement drivers for all of them, but we want to keep the interface extensible and stable, so it is open to contributions from third parties. So as I said, some of these features are still work in progress, but I hope you will see the results very soon. And that's the end of it. I hope that you learned something useful for your next USB Type-C project. The best place to ask questions, look for features, or report bugs is in our ESP-USB repo on GitHub. So see you there. Thanks for watching and goodbye.
Thomas gave us a great deep dive into USB Type-C, definitely a lot of practical takeaways there.
Yes, that's true. And now we are switching gears to something foundational for connected devices. It's data models.
Our next speakers, Amit and Dhaval, will introduce the Runtime Data Model Interpreter, a tool that converts a standard matter ZAP file into a compact, serialized format stored in Flash.
This lets the application and data models be decoupled, and the same format works across different Matter implementations, whether it can be ESP-IDF, Matter.js, RS Matter, CircuitPython, Arduino, and many more.
They'll cover how Matter handles data models and how their interpreter makes building and scaling devices much easier.
So let's welcome Amit Sheth and Dhaval Gujar. The stage is yours.
Hey everyone, welcome to Espressif DevCon 2025. I'm Amit Sheth. I'm an engineering manager at Espressif and part of the team working on two-chip Matter solutions and runtime data model interpreter, which we are going to talk about shortly.
Hi everyone, my name is Dhaval Gujar. I'm a senior engineer working on two-chip solutions, ExpressLink, secure manufacturing, and of course, the data model interpreter. Thank you.
All right. So in this talk, we are going to go over what exactly a data model is, what are the existing approaches of integrating a data model, and how a runtime interpreted approach aids in certain aspects of devices lifecycle. Here, the idea is to treat the data model as data instead of treating it as a code. We have seen in so many IoT frameworks, the data models are baked into the firmware itself, and they are part of the firmware. It has its own shortcomings, such as when you, let's say you want to change devices certain capabilities, you might have to rebuild the firmware or revalidate the firmware, run the regression test on that. This has some impact on the development lifecycle and rolling out OTAs. Similarly, devices, let's say an ODM having a lineup of products, they might have to maintain different variants of the firmware for different SKUs. The aim here is to decouple this data model from the application firmware. Now, before going into what a data model interpreter does, it's essential to understand what exactly a data model is. Now, a data model is essentially a functional hierarchy of a physical device. It represents a device's characteristics, what services a device has to offer. So it also includes data semantics, that is what each data represents. What is the meaning of each data point within the device's data model? And it also dictates how a device or the controller can talk to each other. It defines the interaction rule between a device and the controller that is controlling the device. In a way, it's a digital contract between a device and the ecosystem. Now, there have been various data models that have been doing rounds in various ecosystems. We have seen a BLE, which is most of the IoT devices which are capable of working on. They have a database called GAT database. Similarly, we have seen Apple HomeKit, which uses a database which is called accessory object model, which is a service and characteristic based model, where each accessory is exposing a service such as light bulb, which is made up of characteristics. Similarly, we have Zigbee, which uses Zigbee cluster, which is a cluster library, and of course Matter, which is again derived from Zigbee cluster library, and it has separate concepts such as nodes, endpoint, clusters, attributes, so on and so forth. We'll probably see how a metadata model looks like in a little bit detail. Now, metadata model on the outer periphery, the hierarchically, the outermost is called node, which is a unique identifiable addressable resource in a network. Then comes an endpoint, which defines what exactly the device type is, such as a lighting or a dimmable plug-in unit or a thermostat. It defines what exactly the device type is. Then there is a cluster, which represents what a specific functionality or services the device has to offer. For example, it can be turned on and off. It supports a capability to dim the brightness, to change the level, etc. Then there is something called as an attribute. Attribute indicates what are the various smallest data units that you can read and write to. Then there is a command, which is the commands that you can probably send over network to the device to carry out a specific action or carry out a sequence of actions through a single command. Then there is an event, which is a record of whatever past transitions that has happened and any event that may have occurred on the device. So this is how a traditional metadata model looks like. All the data models we have seen follow similar pattern, which is hierarchical in nature, and which has on their outermost periphery, they represent the device as an overall, and then it goes down to distill into smallest unit which a controller can control. Now I will hand over to Dhaval to explain how ESP envisions metadata model.
Thanks, Amit. So thank you for introducing the metadata model to us. Now let's take a look at how the metadata model currently can be programmed on the ESP32. So there are majorly two ways in which we model the device using tools in the case of Espressif devices. So option one, which you can see on screen, is called the Zap tool. So the Zap tool is a UI which effectively allows you a simplified way to enable or disable characteristics like attributes, as they are called in case of Matter, or you can enable and disable commands. and it also enables all of the things which are mandatory for you out of the box. So it's designed in a way that you would always be able to create a certifiable matter product directly from the Zap tool. So that's option 1. Option 2, which is using the ESP Matter high-level APIs, is defining the same data model using code. So on the screen, the same diagram which Amit was referring to can be modeled using both the Zap tool and also using these high-level APIs in order to describe your device type. So that's the 2 options for modeling the device. Now let's look at how the workflows look in these 2 options. So let's say you have modeled your device in the Zap tool, and now it's time to put it on the device. In the case of connected home IP, the workflow looks like from the Zap tool, you can generate the code. Then you paste all of these files into your application and you modify the application. After that, you build your entire application and flash it and test it. What this workflow looks like in practice is if you want to modify the data model now, you would go back to the Zap tool and go through the whole thing again, which involves regenerating the code, rebuilding it, and flashing it again just to test it out. In the case of ESP Matter, you do not require the Zap tool at all. You can directly write code in order to describe your device. But the workflow looks the same after that, because while there is no code generation involved, you would still need to rebuild your entire Matter application when you want to test a data model change. So these are the 2 workflows and how they look like. Now let's introduce a third workflow. Now let's talk about data model interpreter. The data model interpreter allows you to split the data model from the application binary. So if you look at the flow now, I have a common application which I have built once, and now I can continue to iterate on my data model and flash it separately. So my application, the core application, the Matter application has not changed, but I can continue to iterate on the data model without having to flash or build the entire application again. So that's what it does. Now let's look at how it does this. So there are 2 phases in the data model interpreter. The first phase is serialization. So we already looked at the Zap tool for modeling and how it easily allows us to create a custom device type of our choice, and it makes the mandatory selections for us. So the output of the Zap tool is a Zap file. And in the serialization process, we are able to convert this Zap file into small or low-level APIs, which are creating the endpoint, creating the device type, clusters, and attributes individually. These APIs, along with their parameters, can be written into the data model binary file. So the format which we use is the protobuf, which is an architecture-independent format and extremely space efficient. So what we have done in the data model binary is encoded length value pairs of each of these APIs along with their parameters. This data model binary file can now be loaded onto the module. After it has been flashed onto the module, there is a component which we have, that is the data model interpreter component, which reads back this binary file on the device and is able to make these API calls in order to generate that same device type which you originally described in the Zap tool at runtime. Effectively, in combination, these 2 processes allow you to split or decouple the data model from the application. So let's look at one use case for this. Espressif has a 2-chip Matter solution called EXL. And when we were designing EXL, we came across the same problem. How do we allow customers to customize their device data models, yet maintain a common firmware that we can ship or provide to all of our customers, so that any QA processes testing that we do on the common EXL firmware can be used across the board, and any kind of updates are also simplified for customers. So this is how the workflow looks like. So every customer designs their own data model. It may be air purifiers, thermostats, or anything else that the Zap tool allows, and serializes them into individual data model partitions or data model binaries. So we use NVS as a format for describing or storing the data model binary. and the common EXL firmware on boot up reads it using the interpreter component and loads this data model. Because it's a two-chip solution, the information that it needs to convey to the host MCU is the endpoint ID, the cluster ID, attribute ID, and the value. So with only this information, the host can effectively serve as the application processor and the EXL as the connectivity module. So any updates that take place over Matter can be shared in this format. And the beauty of this format is that it's independent of any specific device type. So no matter what kind of device you make, the same format can be used. And the way we are able to create this common firmware is using the data model interpreter. There is another solution that Espressif offers called ESP-LowCode. And that solution is also a part of one of the sessions in DevCon. So be sure to check that session out. And that also uses the data model interpreter. Now I'll invite Amit back for conclusion, and then we can go for a demo. Thank you.
Thank you, Dhaval, for going over and explaining the two-chip solution and how data model interpreter works. And in conclusion, what we would like to say is the data model interpreter, what it allows is the primary function of it is the decoupling, that is decoupling a data model from the firmware. And it offers varied advantages, where, as like Dhaval mentioned, you can have multiple SKUs using the same firmware while changing the data model. Let's say an ODM having multiple SKUs, they can still use the same firmware and have only the data model partition change to create a completely new device out of it. That's a primary power of separating a data model from the firmware. Similarly, it also allows you to maintain a single firmware for OTAing the entire range of devices, so that you don't have to maintain separate images for each of the SKU or each of the device that you produce. So it avoids that silos. It also allows you to have a better architecture where there is a clear responsibility split between the connectivity module and application processor. In case you have a multi-chip design like the two-chip design, EXL that Dhaval went over. And it also increases the developer's productivity, where a developer can use a very high level tool such as Zap, Web UI to design devices, to create the device's data model and let interpreter do its job and not worry about that at all. For example, we have if you have an ODM, it can only deal with this UI to create the data model that it desires, and then let all the coding and handling of the data model being taken over and being taken care of by the module or the firmware on it, and they don't really have to tweak the firmware or validate the firmware at all. So now we'll probably proceed to a quick demo, a quick short shell session that will be played after this meeting. Thank you. Thank you for watching.
Okay, so I have cloned the Matter data model interpreter repository here. We'll go into examples, any device. I have already built it for the C6. I will just monitor. We can see that the data model is unavailable and that it needs to be flashed at 3E6000. So let's open up the Zap tool. We have two data models here. On the right, we have a color temperature light, and on the left, an air purifier. Let's do color temperature light first. In this data model, the main thing is the color control cluster. So let's try and serialize this now. So we go into the tools directory and we run Python Matter data model serializer -z for Zap, and we drag and drop the color temperature light file. As you can see, the Zap file has been serialized, and we can just check the size of the data model, which is 4 kilobytes. And we already have an NVS binary, which we can just flash at 0x3E6000. And we can drop back into the example now. As you can see, it says commissioning window open. So let's try and commission it now.
So I have a phone here, and I will scan the Matter QR code. Add anyway. And we have the device. So this color temperature light, I can change the brightness level or the color temperature itself. Now let's remove this accessory from the home app. And also factory reset the device by typing Matter device factory reset. Okay, let's change the data model now. So we'll go to the air purifier, which has a sensor, a couple of other sensors, and let's serialize this data model now. So the same command, Python Matter data model serializer, -z for zap, and drag and drop the air purifier this time. So same workflow, and we can see the binary size is now 8 kilobytes. Okay, so we can flash the NVS, ESP tool, write_flash, 0x3E6000, and the path. Let's boot it up again. And just like last time, we have commissioning window opened, and we can commission it now. Scan the QR code. Add anyway. So the device is added, and as we can see, it's an air purifier with everything that we added. So I can change the fan speed, or I can just turn it off. That's all. Thank you, folks.
Hello, and we are back to one more live Q&A. And for this session, I like to invite Davao to join us. Hello, Davao. How are you today?
Hey, Pedro. I'm doing well. How are you?
Yeah, I'm really good. And so, if I remember correctly, this is your third time at DevCon. Is that right?
Yeah. Yes.
Oh, okay. So it makes you a very experienced speaker here at DevCon. So that's
Yes.
great.
That doesn't make the questions any easier, but
Yeah, but you already know like all the flow and how it works, and
Yeah.
so and not only that, it makes you like part of the history, you know, like being part of almost every DevCon.
Yeah.
And I hope to see you next year.
Of course.
Okay. If I understood correctly from your presentation, can the data model binary be flashed separately from the application firmware?
Yeah. So the component design is such that it does not make any assumptions about where you want to store the data model. So I think the way we demoed it is also to showcase the split. But if you look at the way the component is designed, we also have an abstract interface for the storage. So you could choose to store it in NVS, you could choose to store it in raw flash in some specific location, or even get it from the cloud. So we have heard of use cases where people want to download the data model at a later time and enable that. So everything is possible, and there's no specific location from where you need to fetch the data model.
All right. So if I flash a new application, so I don't need to touch the, or sorry, if I flash a new model, I don't need to flash the application, right?
That's right. Yeah.
Oh, that's really nice. And there are any example projects or device already using this interpreter in production?
Yeah. So I think in terms of production applications, the EXL product that Espressif offers, that solution is already production ready and is using the the data model interpreter component and the serialization. The way we use it in EXL is to allow customers to have their own data models. So it's sort of like a bring your own data model concept, where the base firmware of EXL is something that we carry out a lot of testing on, and we try and make sure that it works well across the board. But one thing which we can do, because we have the data model interpreter, is to make a single firmware that we can carry out all these tests on. So we don't have a lot of firmwares to manage. It's just one firmware, and the data model comes in separately from the customer.
Oh, I see. And that's bringing me another question that may impact a lot of people, because certification is a quite sensitive topic. So how does this approach impact device certification and interoperability?
Oh, yeah. So both certification and interoperability are designed around the product. So whether your product uses 2 chips internally, whether the data model is a part of the application, or whether it's separate from the application, all of this is immaterial to the concept of certification. From the perspective of the certification, if anything on your device changes, then you need to recertify the product. So what this means is that even a data model change will require a recertification from the CSA's perspective. So if you have different devices which all have different data models, you can have the common firmware, but you will still need to certify each of these device types. So the common firmware as of date cannot be certified as a firmware that ships without a data model. But if you certify each of these firmwares with their corresponding data models, you would be in a position to maintain continue to maintain a single firmware and use these data models in a dynamic fashion.
Okay, so in another way, it makes things easier.
Yes.
Okay. Okay, so that's good for everyone to know.
Yes.
And we have a question here from Art Maker. So as said, Zap tool can be used to change any endpoint and just flash the Zap file. But about the code that reacts to the different endpoints, the code always must deal with it beyond Zap model?
If I understand the question correctly, yes, there are cases where you will need to do things on the driver side based on the update. So, for example, if the data model update that has been carried out by the controller asks you to change a particular attribute or a particular value, then it might require updates across. And this will require change on the driver side. Now, the way EXL does this is offloads this entire driver to the host. So even if the code needs to change, it's not a code that changes on the data model side. The code which changes is on the driver side. So there's no code that needs to change based on the data model. I mean, you can write code on the host side that does not make assumptions about the data model. I hope this answers the question.
Yeah, so I'd like to ask for Art Maker if the question was answered, just or if you still have question, just leave in the chat. We will try to answer later on. So since we have no more question, so Otavo, thank you very much for bringing us this topic. It was very nice to see how things are getting easier for the developers, not only for Matter, but we are seeing like a lot of talks that shows how we are making developers' life even easier. So thank you very much.
Thanks, Pedro. Take care.
Yeah. All right, now we can go back to the program. Thank you.
That was a great look at data models, super clean explanation from Amit and Dhaval. Now, we are wrapping up today's talk with something a lot of developers will appreciate, making OTA updates painless.
Exactly. Our final speaker for today is Chip Weinberger, the creator of Otavo, and he built it because he was simply tired of writing OTA code over and over again.
Otavo is a drop-in OTA solution for ESP32 devices. No boilerplate, no weird edges cases, just reliable updates.
It supports pretty much every transport you can think of. It can be BLE, Wi-Fi, SD card, UART, or it even lives in its own dedicated partition, making it super reliable and easy to integrate.
It's currently a B2B tool, but a free version minus encryption, it's on the way, which is great news for the community.
Yes, so let's welcome Chip Weinberger, our final speaker for today's conference lineup. Chip, the stage is yours.
Hey guys, let's jump right into it. This talk is about Otavo, a better way to do OTA updates on your ESP devices. Now first, why should you care? Well, it's because OTA is a pain. It's super high stakes. If you screwed up your devices, it could be inoperable and cause you a lot of money. And everyone needs to write it themselves, which is a double whammy. Well, what if I said we could solve both of those things and completely fix them? That'd be pretty nice, right? Well, who am I? I'm Chip Weinberger. I'm an engineer, and then I was a product guy, and there's my email. And I've gone through this OTA pain. This is my product. It's called Jamcorder. It's a device to record digital pianos. So I know this pain well. I've also been pretty active on the ESP-IDF, and I have a few PRs that have been merged. This one was, despite the closed. This one's for async HTTP and a couple of more that I'm hoping to get merged. And before that, I worked at Apple on the Photos app. So let's get back to OTA on Espressif chips and how we could make it better. A refresher, OTA, that is when you update your firmware on your device. You have a computer of some sort, your phone, your own computer or server, update the firmware. We all know this. And the firmware can be sent a million ways. Here's some common ones. And it uses A-B partitioning. And here's how it works. We have A, update B, right? A is running, B is updating. Pretty familiar. And then we flip it around. If B is running, A is updating. We should all be pretty familiar with this. It's a nice, simple model. We only have to concern ourselves with a single binary. And we only have to update one binary. Which is nice. We only need a single Git repo. You get easy rollback. If B is broken, you can roll back to A or vice versa. But it's actually not as rosy as it sounds. There's a lot of disadvantages. First, it doubles our storage. That's a pretty pricey one. We got to pay for that storage. And this is really going to be the entire focus of this talk. This is the major downside. It is tightly coupled to our application, and we'll see all the various ways that is not good. To drive that home, what that means, it means in our A partition where we have our application, you have your OTA code and you have your app code, and they're all in the same binary with a bunch of common code. They're compiled together. And that's really bad for one big reason. It means we can't have someone else write that OTA code. It's going to interface with our own code, and we're probably going to have some way of triggering that. Maybe this is hypothetical, but maybe we have a process commands, and when we see the update command, that's when we run our OTA code. So we're going to need to write some code to integrate into this OTA. We can't, even if we had a third-party library, we're still going to need to interface with that third-party library. And that's just really the tip of the iceberg on the coupling. Because we have a single binary, they share all the K configs, they share all their memory, they share their peripherals. If they're both using USB, well, one's going to have to stop using USB. Can't both use USB at the same time unless they're smart about it. Same with Bluetooth or Wi-Fi. They have to be smart about how they share these peripherals. UART, whatever it is. That's going to be pretty complicated pretty quickly. And you're also going to need to do some error handling if things go wrong, and your application is going to need to do that. and they're on a level above the peripherals. The protocols could also be shared. Each peripheral has a various ways of doing protocols, but that's just one level above. So what does that mean, that tight coupling? This is not good. All our app updates also affect our OTA code. You might have not changed your OTA code. You're like, yeah, I don't want to touch that code, right? Because that's like really high stakes code. That's not the kind of thing you just willy-nilly touch. Well, I hate to break it to you, even if you don't touch it, it's still gonna be affected for all those various reasons. You change a K-config, okay, OTA code changed. You allocated more memory. Okay, OTA is now slightly different. It has less memory to work with. Maybe it has more fragmented memory. You change how your peripherals work, right? All these things affect your OTA code as well, especially if you change like the common code underneath. So it's just unavoidable. If you compile them into the same binary, there's no way around this. Your app updates, all your OTA code gets changed. And this can really come to bite you. Let's take a look at how this can work. We start with A and B both having the same code in it. They're identical. Well, you do an update, and you change your memory. You change the K-config. So now the OTA is slightly different. Hopefully not by much, just slightly different. Now you do the same thing, update that partition again, and you change another K-config, or you change how a peripheral is used. And now that OTA, you didn't mean to change it, but it's like the timing's off or something. And it's subtle, or maybe it's not subtle. Maybe you change the common code and you kind of knew it was going to change. But your OTA is slightly different again. You do it again, you have more OTA differences. Wow, we now have 4 different OTA versions. Maybe this happened quickly. Maybe this was over the course of years that these changes happened. But because they're tightly coupled in our application, they're bound to happen. And what does that mean? It means that when our computer goes to update our ESP32, it can't just blindly know what OTA code it's running. It has to look at what versions it's running and then make sure that it runs the compatible OTA update software. Hopefully these are all very similar, because who wants to maintain 4 different ways of doing OTA? But these mistakes happen. I mean, it's software development and we're not perfect. And there are real companies that make this mistake. Here's SpaceX. They're pretty smart guys. Look at these support. My experience with a brick dishy. Support told me to throw away my working but out of date Starlink. Wow, a $500 support told them to throw away a $500 dish. And why? Like, what happened? Well, it's not that anything was really broken on the Starlink. Actually, the Starlink was working fine. It still had a completely fine working OTA. It's just that their servers, they didn't want to maintain all the various different ways of doing OTA. They stopped supporting this older one. And this guy left his Starlink unupdated for too long. He left it unplugged for like 6 months or something. And it was just running an out-of-date OTA. So they could recover this Starlink, but they probably won't, and that's why support's telling them to throw it away. They don't want to do the engineering costs of maintaining all these different OTAs. So this really bites people. And this happens because it's tightly coupled. There's really no way around it. But let's be clear, SpaceX, they bricked that device on purpose. They said, we don't want to pay that cost. We don't want to do the development to support it. So long. But it's not always how it is. It could be it could be by accident. You could brick your OTA by accident. So let's look at a slightly different version of how this could go and see what mess we end up in. So we have our A and B, right? We're familiar with this, but this is not a real picture. It's actually happening over time, right? A is updating B slowly over time. Well, what happens if B gets halfway and then just stops? And you're like, uh-oh, something's wrong. Why is the firmware not finishing? Well, regardless, it's not finishing, and B is broken. Until we can finish that update, B is inoperable. And you're like, what did I change? What could possibly have broken this? Oh no. Well, you look through it and It turns out you changed a little bit of common code. Oops, you didn't realize it was being used by the OTA code, and it causes the crash halfway every time. Oh no. That's not good. I mean, take a look at this picture. You have a broken B partition, and you have a OTA code that was accidentally broken. And now what? How are you going to recover from this? It turns out you can't. I mean, without a debugger or some supporting hardware, your customers are not going to enjoy getting out of this mess. It'll probably be better just to have them send the device in. It's going to get really expensive. But at least they still have their A partition, which is hopefully somewhat usable, because that's what they're going to be stuck with forever. They have a bricked OTA, and they're stuck on that old firmware forever. So hopefully that firmware was decent, because you're not going to be changing it. That's a terrible scenario, and that is the kind of scenario you can get into with this A-B partitioning. And let's rewind a bit. What are the various ways that scenario we could enter it? We touched on some of them. Maybe we have shared memory. So maybe the application was using too much memory. We didn't realize that when we allocated an extra half meg, the OTA wasn't going to have enough halfway through. Oops. Maybe your app is crashing. You have a timer. You're doing something every few minutes. And it just crashes after 3-4 minutes and you didn't notice. Your tests didn't catch it. And that's not enough time to do an OTA. It always crashes halfway done. We touched on this one. Maybe you change your common code. Maybe you change your OTA. Oops, like that one, you probably should have tested that one a little better. Maybe just change your OTA. So there's a lot of ways you could enter into this terrible OTA brick scenario. But I want to be clear, if your OTA is not always bricked, if there's some way you can get out of it, maybe you do a factory reset, maybe you turn off some features, hopefully you can do something to get that OTA working again. Hopefully there's something you can do. Because if you can get that OTA working, then we can recover from it. We can update B, and then B can fix that OTA, and we can get back into a good state. So hopefully that's the scenario you find yourself in, but it might not be. And who wants to deal with that? Oh my God, that could be the end of a company. That could be the end of a company. So it brings us to a big question. With the stakes so high, why are we changing our OTA willy-nilly when we don't even intend to change it? Don't fix it. It ain't broke. Don't fix it. We all know this. So stop changing that OTA code. Well, how could we do that? How can we decouple it from our application so that we never break it? Well, here are some things that we would want in a decoupled OTA system. If let's let go of the A-B partitioning for a second. What would we want? We would want to have a separate OTA mode that never changes. We validate it once and don't fix it. We want it to be its own binary. Again, it's decoupled from our application. It's the same point. And we want to put a lot of features in there, or at least all the ones that we could ever expect to get us out of. This is our recovery mode. And we want to have at least a few different ways of recovering, ideally. So that if a customer has a broken Wi-Fi card, and they could do it some other way, Bluetooth, then they could do Bluetooth. That'd be a nice feature to have. So we want to support all the different ways. And we also want to be rock solid. We don't want to depend on lots of state and NVS. We don't want anything that could potentially break it. If you go into this mode, it should basically do the same thing every single time. So we only need to test it once, and there's no permutations. And we want it to be small, so there's more room for app, and it should be tested extremely well, right? Because we don't want to brick everyone's device. And if it's battle tested, why would we change it? We've been over this. Don't change it. But you could. I don't recommend it, but you could. Let's just be clear. There's nothing preventing you from changing it. If you want to make it faster or do something like that, you could do that. So we want to cover all these let's rewind a little bit. We want to cover all these, right? Has anyone ever done something like this before? Well, it turns out, yes. DFU mode, it's found on lots of devices. This is how it works on many devices. They don't have an AB partition on your iPhone, on your Android phone. They don't, Android has changed a little bit over time. I'm not sure what they do these days, but certainly not on iPhone. You don't just have a completely, you don't half your storage. You just have a small little recovery mode. That's how it works. This is the same way Otavo works. And the same for on our desktop computers. We have recovery modes on Windows, we have them on Mac, and they're decoupled from the OS so that we can fix the OS. And even our cars have them. So we need a DFU mode for ESP32. Let's move away from this AB that's taking up half our storage. Let's just make it a better DFU mode that everyone can use. And well, I'm putting out my first implementation of a DFU mode for Espressif, and it is called Otavo. So let's take a look at what that looks like. If it's not clear already, Otavo is a separate partition. You only have one of your app partitions. You could theoretically have 2 or 3 or whatever, but there's only going to be one Otavo partition that updates your app or updates multiple of your apps. Ideally, it never changes, but it can. Your app could update it, but the whole point is make it work once and work on other stuff. In fact, you don't even need to write it. It's already been written, even better. So let's take a look at how that update works. You boot into Otavo in some way. You have to trigger it, maybe push a button or something. Otavo updates your app, and then it reboots back into your app. All right, so there's two boots. Boot into Otavo, boot back. Pretty easy. What about rollbacks, right? We had AB before. That was a pretty nice feature, right? If something was broken, we could just jump to the B partition. Well, we get the same thing. It is, if the B partition's broken, just set a flag and reboot back into Otavo and have Otavo restore the previous firmware. Or more precisely, have your server or your application detect, oh, hey, it booted back into Otavo. That's not good. Let's check for that flag. And I guess we'll have to do a rollback, right? You can do rollbacks. It's just the same. It takes a little bit longer, but you still can do the rollbacks. It's no big deal. Big question, right? Can we really do this? It sounds like a nice idea. Does it actually work? Well, yes, this is exactly how Jamcorder works. I didn't want to go through the SpaceX scenario. I was deathly afraid of bricking all my devices. I didn't want to even take the risk of changing my OTA code. It was just, that kept me up at night. So I said, I'm going to write the OTA code once and be done with it. And that's how Otavo was born. So this is in use right now. It works, and it works amazingly. It gives you all the things that I asked for. And I even added AES firmware encryption, which is another thing I needed. So all the updates are encrypted. And that's the best part. It's written for you. It's decoupled from your app. So you can just install it without needing to write any code in your own app. Like, that is a huge unlock. That's huge. That saves you weeks of time. You can just use Otavo for your OTA updates. So let's take a look at how some of the updates work. These should be pretty familiar if you're in OTA code, but it's good to get a better idea of how this works. So the first one, SD card, right, familiar. Otavo supports SD card updates. Put your firmware in an OTA put your firmware somewhere on the SD card, and Otavo will look for it and update. And a little fine detail though, this is really key to what makes Otavo so reliable. It doesn't look at this location. It doesn't even load. It doesn't even load the mount, the SD card, until you reinsert that card. You have to pull that card out, put it back in. Or if it wasn't already out, you just got to put it in. Because the whole idea of Otavo is it's going to be super reliable because it has very few inputs. SD card manufacturers are all a little different. You don't want to mount one. Just mounting one could cause a crash. So you don't want to mount one until you know. So how can we how can we make it so it does the same thing every time? Or doesn't do anything that might crash, right? We do not want this to crash. How can we do that? Well, we have to reduce the amount of complexity. So not mounting the SD card until the insertion, that's number one. We want to have very few inputs. What about MVS? We don't want to use MVS, right? MVS is from our application. It's always changing. Otavo does not use MVS. We don't want any persistent state. We don't want to mount the SD card because all SD cards are a little bit different. They might crash us. We don't want to, file systems are all different. We don't want to traverse the file system. We want as little state as possible. And Wi-Fi, Bluetooth, those all use airwaves, right? We can't control the airwaves. They all could theoretically crash. Maybe there was a packet. We tried to parse a packet. Oops, crashes. So we need a way to disable those things. And Otavo has a way to disable them. So you can always get back to something that's working. Something with very few inputs. So how would it work over BLE, right? Well, you connect to Otavo over BLE. You call this progress endpoint to see if there was already something running. And then you start uploading chunks. It's chunk-based. It uses HTTP over BLE. And then you call reboot, right? Pretty simple API. You check if there's any progress. If you upload the first chunk, it'll restart from the beginning. And if you upload the next chunk, it'll continue. And if you upload the wrong chunk, it'll give you an error in return. You just upload your chunks until it returns done. And then you call reboot. Pretty simple. But one fine detail, because we're doing this multiple reboots over wireless and doing wireless communication, we need a way to connect to the same device. We need to have the BLE advertisements stay the same. We need to have an ID that we know is always the same. So Otavo uses a 128-bit UUID stored in a separate JSON partition. This UUID is generated by the application or by Otavo. If it doesn't find it, or if it's the wrong form, it'll generate this. It's a very simple partition, which is actually cleared on factory reset. But we need some way to have an ID stay the same between both applications so that we know how to find the device. And we use that ID in the BLE advertisements, also in the Wi-Fi access point name. So let's take a look at that. How would it work over a hotspot, Wi-Fi access point? So your device advertises a hotspot. That works too. You could do an update that way. So you advertise your hotspot with your UUID in it, your application or server, your client device connects to it and calls the same APIs. It's all the same APIs, which is really nice. And there's even a web server built into it. Otavo has a web server, so you could just drag and drop your OTA file onto the web server. So you don't even need a separate device. You get this for free. Of course, there's also Wi-Fi STA mode, so you can have Otavo connect to a Wi-Fi access point. This one's slightly different because that is a little bit of configuration. Not everyone's going to have the same Wi-Fi access point password and name. So you're going to have to, from your application, you'll first need to configure what is the station it needs to connect to and the password. And that is a little bit of state. We clear that state on boot. So if you were to reboot twice, that would be gone because we really want to avoid state as much as possible. No persistent state. We'll use it once on boot, boot args. It'll be our one-time boot args, our password, and that's how you can do it over station mode. And of course, we have it over serial too, and it uses all the same API. All the APIs are generic over all the peripherals, so you don't have to learn much. Here's a little preview of the API and some of the K configs that you can set. And we might be asking, well, what about a remote HTTP server? I want devices to connect to the internet and remote and connect and update that way. Well, Otavo does not support that. Maybe later, but there are various solutions for that. We don't need it, and it's a bit more complicated. I built this thing to be rock solid reliable. And this is, I didn't want it, didn't need it. So, but maybe later if there's demand for something like this. So let's take a look. Let's look at it running. 12-second demo. Let's rewind just a little bit. That first screen, we see there's an update available. Firmware update required. The application says, okay, there's an update. Let's do our update. It reboots into Otavo. It applies the update to our partition, and then it reboots back into our application. Very simple. Hardly any different than a AB partition. There's a one extra reboot. And for that one extra reboot, you get all those extra features. Reliability, decoupled. It is the DFU mode. The DFU mode style is such a better way of doing updates. So you're ready to integrate this. You're like, I want this. What do you need to do? Well, you need a way to boot into the Otavo partition. And you need a way to send Otavo the update. Let's take a closer look. You need to boot into it. You need to trigger that update somehow. If you're using any of these protocols, then you'll probably call a command of some sort. So this is the one I use, API OTA reboot into, and that will use the ESP-IDF commands to reboot into my Otavo partition. Very simple. You do have to write that, assuming you want to be able to trigger this remotely. Not have to have a user push a button or something. If you want to be able to have that API remote, you'll have to implement that. Or you could have a physical button that the user pushes. Or Jamcorder also has something called safe boot. You could implement something similar, which if my application fails to boot for like 3 times in a row, it'll reboot back into Otavo. But you need some way to boot into Otavo. Any of these will do. That's the one thing you need to do. Very tiny. And you need a way to send it the update. This one, again, you're using those APIs to send it those chunks. You'll have to write that. That's the most involved part. But you're gonna have to write that anyways. Or you could do it via SD card. Or you could even do it over that web server that I showed. But presuming you probably want to do it from an app, you'll have to call the APIs. But the APIs, there's like 2 of them. It's progress and upload chunk. Not much to it. So you're convinced. I hope I convinced you because it is such a nice way to doing OTA updates. And you want to know where to get it. Well, just go to otavo.xyz. It is currently for commercial users, but it'll probably be opened up to free users on GitHub at some point. But if you're a commercial user and you're interested in it, please reach out. This is a new product, and it's really helpful to know who's interested, how much interest there is, so I can keep on working on this, and we can really make this thing purr. So please reach out to me if you're at all interested. Thank you so much. Bye.
What a fantastic way to wrap up today's sessions. Huge thanks to Chip for that great talk, and of course to all our speakers throughout the day. We covered everything from UI and AI to multimedia, Type-C, OTA, Matter, Vision, and so much more.
Yes. Today really showed just how much is happening across the Espressif ecosystem. Whether you are building smart cameras, connected devices, secure Matter products, or just experimenting with AI, there was something for everyone.
And the best part is we're not done yet. Tomorrow we have something a little different lined up.
Right. So day 2 is our live session. No slides, no pre-recorded talks, just an open interactive session where you can join us live with Ivan, ask questions, share feedback, and hear insights straight from the people building the technology.
It's a great opportunity to dig deeper into anything you saw today, or even bring up topics we haven't touched on yet.
So make sure to join us tomorrow for more conversational hands-on session. Bring your questions, your ideas, and maybe even your wish lists for the future features.
Thanks again for spending the day with us. We hope you enjoyed the talks as much as we did.
Have a great rest of your day, and we will see you tomorrow for the live session with Ivan. Thank you.
Bye-bye.